That's better. Yeah. So welcome, everybody. And thanks to Sabila Alibhai, Conn College class of 2025, recent grad from the Goodwin-Niering Center for the Environment, for the music. I got to say, Sabila took a course with me last year that was on aesthetics and nature, and I didn't even know that they could make music like this. So it's just wonderful. Thanks, Sabila, for joining us today. Welcome, everybody. My name is Derek Turner, in case we haven't met. I'm a professor of philosophy here at Conn College and serving as Carla Hirek-Harrison, class of 28, director of the Goodwin-Niering Center for the Environment. I would like to open by reading a land acknowledgement this morning. We acknowledge that the land we currently occupy we acknowledge the land we currently occupy and honor the native peoples who were its first inhabitants. Specifically, we honor the Mashantucket Pequots, the Eastern Pequots, the Mohegans, and other native nations who are indigenous to Namiag, now called New London, and the land surrounding coastal Algonquin, also known as the Long Island Sound region. We acknowledge that indigenous peoples have cared for this land over many generations and know that they endured suffering and violence through the historical period of settler colonialism and its legacy. Today, we strive to tell and retell the complete stories to repair the harm and to live together as neighbors in this region. So I apologize for those of you who were at the event, the kind of opening event yesterday. I might repeat a couple things that I said yesterday, because I got to say a little bit about the center. I got to say a little bit about Dick Goodwin and Bill Niering. Our center is named for these two legendary botany professors. And anyone who's interested, I can now take a selfie with them up in the art gallery. That's Dick Goodwin and Bill Niering up there. Our center supports faculty-student research and advocacy on environmental issues. And students in the program, including some of the students you'll meet today, complete service learning projects and environmental internships, and they undertake significant independent research or creative projects in the senior year. And one quick shout out, if anyone's around on Thursday, April 23rd, the seniors in the center will be sharing their work over in Olin Hall starting at 4:30 in the afternoon. So it's a great chance to kind of see what the students are working on in a couple weeks. I'm really excited to welcome everybody to our symposium on sea level rise, understanding, measurement, and adaptation. It's kind of, I think about this all the time. It's a real privilege just to be here at Conn at all, where we have this kind of amazing tradition of research and coastal salt marsh ecology, which is super connected to sea level rise. And that goes back to Bill Niering, for example, who is a coastal wetland ecologist. There's been a number of faculty at Conn over the years who've done work on salt marsh ecology, so Scott Warren, Pam Hine, Paul Fell. Biologists today in our department are working on questions about salt marsh systems and sea level rise, so Maria Rosa, who's here, and Ann Bernhard. So it's a pretty great tradition, and I'm just excited that that our symposium is one more part of that. We are really jazzed to welcome 5 distinguished speakers to campus, and you'll hear from 4 of them over the course of the day. I just want to mention Dr. Kelsey Leonard is here from the University of Waterloo. Katie Serafin is back from the University of Florida. Tammy Lewis from CUNY, Brooklyn College. Christopher Paikush from Woods Hole Oceanographic Institute, and Elisa Bakulich from Boston University is with us this morning. So thank you all, big thanks for joining us today. We're really excited to hear your talks. I'm gonna just take a quick second to share a thanks to the generous donors who make it possible for us to do this. You might have noticed this is the Lear-Conant Symposium, and we're grateful to Linda Lear, who is a distinguished environmental historian and biographer of Rachel Carson and Beatrix Potter. She's Connecticut College class of 1962, and she's been just a wonderful friend to the college and the Goodwin-Niering Center. And I think it was Linda Lear's idea to name the symposium to honor another kind of luminary from the college, Elizabeth Babbitt Conant, who's Conn College class of 1951. If you haven't heard of Babs Conant, as she was known, she just had an amazing career. She was an interesting biologist. She studied African lungfish and did cool research on them. She was a dean here at the college for a while. She was on the board of trustees, so really, really interesting person. I want to briefly thank the team that helped put this together. So in the Goodwin-Niering Center, we are just really fortunate to have amazing colleagues. So I want to give a quick shout out to Jen Lamb, who is the staff director of operations up in back. Jen, Professor Julia Flagg in sociology and director of environmental studies is up here, also helped us a lot with the planning. Professor Doug Thompson in environmental studies and earth sciences has done a ton of work to kind of help out. Professor Maria Rosa in biology, there's Maria, also has been involved at every step of the way. And most importantly, the person who's really done the heavy lift to make all this happen is Kelly Wagner, our assistant director of the Goodwin-Niering Center. Is Kelly around? Kelly, we got to give Kelly applause. I don't know. I don't see Kelly. She may be off doing work to make sure the next thing in the day. she's been working like crazy. So anyway, thanks to everybody who's helped out. Thanks to everyone who's helped out with the tech. Thanks to the catering staff, custodial staff, everyone who's been a part of this. A couple specific thanks to Jeff Gata and Meryl Collins, and Christina Flowers in communications has also helped us with getting the word out. So, good. Also thanks to some of the current students who've been helping Kelly with setup and everything. Thanks again to Sabila for music. One of our current students, Pluto Shea, has worked up a playlist for lunch, actually, which we're looking forward to. And I wanted to say thanks to a recent graduate, Sadie Abu Haidar, who provided the artwork. We gave Sadie the task of just creating 3 pieces of artwork for understanding, measurement, adaptation. So, good. A couple of quick notes just about format. Each talk will run an hour, give or take. We'll have some time for Q&A after each talk. Then later in the afternoon, we're going to have all the speakers up on stage for a more casual kind of Q&A and panel discussion, which I'm really looking forward to. We have a tradition where we tap our current seniors in the center to introduce each of the speakers. So I would like now to invite the first of our student introducers up to the stage to introduce our first speaker. This is Sam Olstein, who is Sam. Sam is a senior in the center, environmental studies major, has taken some philosophy classes too, and completed a senior research project with Doug Thompson last fall on sustainability issues in the outdoor recreation industry. So, Sam.
Good morning, guys, and thank you, Derek, for inviting me up to stage. Hi, my name is Sam, and today I'm here to introduce Christopher Pykush from the Woods Hole Oceanographic Institution. Chris is a passionate sea level scientist and ocean circulation scientist and educator, currently running his own research group, mentoring young scientists in ocean research, and teaching a joint program with MIT in oceanography and applied ocean science and engineering. Chris's resume does not end with his work in Woods Hole, as he's also an accomplished scientific writer and speaker. Chris is currently the associate editor at the American Geophysical Union's journal Earth's Future, and has been published in multiple other peer-reviewed journals throughout his career. Chris's outreach extends to non-scientific audiences, demonstrated by his appearance in the New York Times, the Washington Post, and the National Public Radio. Throughout his career, Chris Chris has collaborated with state, national, and international teams on a range of topics in sea level science, having briefed the Office of the U.S. Special Presidential Envoy for Climate and the Office of Global Change, as well as assembling panel discussions on coastal risk and sea level rise, geared toward policymakers at the United Nations Climate Change Conferences in Egypt and Dubai. In summary, Chris has worked to advance our knowledge of oceanic changes in support of more resilient and prepared coastal communities in the face of rising seas. I'm honored to invite Chris to the stage to deliver his lecture titled Coastal Sea Level Acceleration and High Tide Flooding in the United States.
Good morning, everyone. That's me. Yeah, thanks for coming. Thank you, Sam, for a really kind introduction. Thanks, Kelly and Derek and everyone else at the GNCE for putting this event on. I think you have something really, really special here. I also want to thank Katie Seraphin for the really inspiring and fantastic talk she gave last evening. So hopefully a lot of you were able to be present for that, and congratulations again, Katie, on the award. There we go. The talk I'll give today touches a bit on all three themes of the symposium, on measurement, understanding, and to some extent, adaptation. And I wanted to explain the terminology in my title, because it might be similar but a little bit different from words that you may have seen before. So I'm using the word sea level acceleration to indicate, as I'll show, that yes, sea levels are rising, but they're not rising at a constant rate. In fact, we've seen them increase over time. That is, the rate of sea level rise is itself rising. Okay, I'm calling that sea level acceleration. And I'll also talk about this idea of what we call high tide flooding. Now, if you were present for Katie's talk yesterday, she was really focused on these extreme events, these 1-in-100-year type storm events, these things that have a large impact on communities. And that's a really important avenue of research. And in addition, what you'll see is that due to sea level rise, we're also seeing an additional kind of flooding that's emerged over the past couple of decades, which we have variously called high tide flooding, king tide flooding, sea level rise flooding, sunny day flooding, you name it. And it's much more low level. And we'll talk about that a bit. So again, my name is Chris Paikush. I'm at the Woods Hole Oceanographic Institution, where I study ocean circulation and sea level. But before I get into the science, I do like to start my talks with a story. Does anyone know where this photograph was taken? Yeah, where? That's right, in Annapolis, Maryland. So it's the city dock down at Annapolis, Maryland. What we're looking at here is the Alex Haley Kunta Kinte Memorial that was put up decades ago to commemorate. So Alex Haley, of course, is the author of the book Roots in the 1970s. And here the author is shown reading from the book to three children. It's this monument to racial reconciliation in this country, and the author's hope for that. And it's also really a poster child or a really poignant example of climate change. Because you see, when the monument was placed decades ago, the elevation where it was placed was about 8 or 9 inches above highest astronomical tide. That is the highest level of the tides you'd expect under normal conditions in the absence of storms, okay? That doesn't look like it's above highest astronomical tide. As I'll talk about, due to sea level rise, water levels that we used to see very infrequently are now commonplace. If you Google Annapolis and the Alex Haley Memorial, you'll come up with any number of photographs just like this. And a key difference, actually, to relate this to Katie's talk. So Katie was talking about waves and these really extreme events. What you notice is that, sure, there's a little bit of wave action here, but the waters are pretty placid. So this is a very different kind of flooding than what Katie was talking about yesterday. Now, I pick Annapolis because I think it's a really poignant example of this phenomenon, but I really, frankly, could have chosen any community on the U.S. East Coast. Here's some more examples from Miami and the Florida Keys and Washington, D.C. After conversations with Derek yesterday, I probably could have chosen Mystic, Connecticut as well. Communities up and down the U.S. coastline are experiencing these kind of events. So I'm going to shift now from talking about stories to talking about statistics to kind of put this in perspective. Because again, the story here is sea level rise, okay? And the amount of sea level rise we've seen since the turn of the 20th century, we know that that rate was faster than any other century period in at least the past 3 millennia. Okay, this is research that was first published about a decade ago, that was tweeted by then President Barack Obama. It's been corroborated by subsequent research, and it's one of the headline conclusions of the most recent Intergovernmental Panel on Climate Change report that was released a few years ago. So what we're seeing now in terms of sea level rise is something truly unique. Here are some of the data that go behind that statement. So just to orient you to this graph, I'll be showing lots of charts and graphs. So just to orient you to the lay of the land here. So I have time running along the bottom, going from past to present, left to right, in years common era. And on the horizontal or y-axis, I'm showing the rate of sea level change, and I'm giving this in units of inches per century. And this is a global measure. And what we'll see in a moment is that what's happening globally doesn't necessarily reflect what's happening locally, but global sea level change is a really informative measure of climate, okay? So here's what we see in terms of the rate of sea level rise over the past 3,000 years. Before the Industrial Revolution, you don't see a flat line at 0, so there certainly was sea level change in the past, and it sort of goes up and down by maybe plus or minus 1 inch per century. That is, of course, until you hit the Industrial Revolution in the mid-1800s, and you see a skyrocketing of the rates of sea level change. So this is a visual demonstration of just how unique current rates of global sea level are. So I've motivated this with some storytelling and some data and statistics, but I want to pull back now and give you a sense of where I'm going to be going with this talk. So I really want to answer 3 really basic questions about sea level rise. How do we know that sea level is rising? What are the data and observations that we use? This is again going with that theme of measurement. Why is sea level rising? What are the causes of sea level rise? I'm kind of obsessed with one of the graphs that Katie showed yesterday with the little Lego pieces, so I'm going to come back to that in a little bit to advance our understanding of sea level rise. And then the final question is, and this is the adaptation-related one, is what next? What do we do with this knowledge? So the first question, how do we know that sea level changed in the past and that it's changing now? So just a second ago, I made a statement and showed a graph about sea level change over the past 3,000 years. And in order to make that statement and to produce a graph like that, I need data. So what are the data that we use? Well, it's not a trivial question, because if we're talking about past change in the Earth system before industrialization, before the past couple of centuries when human beings started systematically, instrumentally observing their environment, where are we going for the measurement? So this is where we turn to natural archives. So some of you may be familiar with the use of tree rings in climate research. So every year, the story goes, trees will grow a new ring, and that the material that's incorporated into that newly formed layer will reflect the atmospheric chemistry of the time, thereby providing a measure of changes in climate. So in sea level research, we don't use tree rings, really, but there are other sort of features of the natural environment around us that, by their very nature, keep track of changes in sea level. And Derek mentioned one of them a second ago, which is salt marshes. And we'll talk a little bit more about salt marshes and how they help us record past sea level, but also environments like mangroves, if you're more in places like Florida where Katie is, or places like coral microatolls. So I'll talk more about the salt marshes because that's what I have worked with in the past and know most about. So salt marshes are really phenomenal coastal environments for a variety of reasons, for their aesthetics, for the ecosystem services they provide, but also because they provide a record of past sea level change. Because provided that sea level rises within a certain window, salt marshes are able to accrete and sort of gather sediment and grow vertically and keep pace with sea level rise. So the process that you have is that continually you're depositing a new sediment layer on the salt marsh platform and building up a time capsule such that the deeper you go in the salt marsh sediment, the further back you go in time. So if you were to go to a relatively undisturbed marsh, which isn't necessarily easy to find, but if you go to an undisturbed marsh take a core of the sediment. Like I said, you have a time record of change that allows us to say how high sea levels were in the past. And we do that in two ways. One is that we have to date those layers. How long ago were those layers laid down? And we're able to do this through radiometric dating. We find particulates of organic matter that we can date through radiocarbon, and that provides a measure of how long ago that layer was laid down. But we also need to know where that layer sat with reference to the tides. And to do that, we scrutinize tiny microfossils, foraminiferal fossils, which have, in the present day, very well-established tolerances to different tidal regimes. So that provides us a measure of where that layer was relative to sea level. So with that information, with the foraminiferal species and radiocarbon dating, we're able to put together figures like this. So again, we have a similar orientation of this plot. We have time along the bottom and a measure of sea level along the vertical axis. Now we're going back 5,000 years into the past, so we're looking at the late Holocene period. And then we have meters of sea level change on the the vertical axis to the left, where I'm calling present day 0. Okay, so present day is 0. And each one of these dots marks the height of sea level in southeastern New England. So these are all from southeastern Massachusetts and Cape Cod. Each of these square circles marks the elevation of sea level relative to the present at some point in the past. Okay? And what you can see is that, yeah, sea level has been changing long before humankind started becoming a force in the climate system. And what we see is that the orientation of these squares is from the bottom left to the top right of the graph. Okay, so we did see rates of sea level rise on the order of multiple meters over millennia. Does anyone know why this is happening, or why this happened? No? This is a vestige of the last ice age. Okay, so 25,000 years ago, much of New England and much of North America was covered in ice sheets. Okay, that system started deglaciating between 10 and 20,000 years ago, and by about 7,000 years ago, we had lost most of that ice. And the analogy I give here is that imagine you're going to bed at night, and you lay down on your mattress, and the mattress sinks beneath you and sort of assumes your form. Okay, so when you have these giant ice sheets, and I'll talk more about this later, as you depress that surface. But then when you get up in the morning, your mattress resumes its former shape. It rebounds. Okay? The Earth does the same thing, but it takes a whole lot longer. So even though all that ice melted by about 7,000 or 8,000 years ago, we see the ongoing, what we call post-glacial rebound effects, which cause a sea level rise in this region. So what we're seeing here are these rates of post-glacial rebounds, which start to taper off as you get to the present. Okay, so this is the picture in southeastern New England. You can obtain these data from multiple locations around the world in the East Coast, and here's sort of a bar plot that illustrates rates of change over the late Holocene, that is the past 4,000 years or so, from the northeastern US, where we are, all the way down the coast to Cuba and Puerto Rico. And what's interesting, again, we have the rate on the y-axis, and I'm a scientist, so of course I'm putting this in millimeters per year, which is like, what is that? So to kind of put that in other terms, 1 millimeter per year, if that rate persists for a century, that's about 4 inches. So a rate of 1 millimeter per year, you can kind of think of that in a centennial sense as 4 inches of rise. Okay? So we see our rates of change over the late Holocene on the order of 1 millimeter per year, or a few inches per century. But the height of these bars isn't the same. It shows some structure such that you get the highest rates along the mid-Atlantic coast, and then as you move south or north, those rates taper off. And that's not some artifact or error with the data that we're working with. This is a genuine feature of the nature of sea level rise. And I'm going to come back to this in a few moments. So this is just a taste of the kind of data that we can use to infer past rates of change before human beings started systematically observing their environment. If we're interested in more recent change, we can avail ourselves of more recent measurements, and this technology has been alluded to in the brochure, in the advertising material for the symposium, and I think in some of the talks, certainly Katie's yesterday. One of the most important data sets we have of sea level change, both in the US and globally over the past century or so, are tidal gauges. Okay, so I've given some photographs of some example tidal gauges around Massachusetts and Rhode Island. And in principle, these are really, really simple devices. Historically, you'd have something like a PVC pipe with a flotation in it that would sit on the ocean surface, and it would be attached to basically a string, to a pulley, to a rolling drum, and it would sort of rise and fall with the tides and thereby record changes in the tidal levels. I say it that way because really the focus when these things were installed was the tides. They weren't put in for scientific research, they were put in more for navigation and commerce periods, when do you want to bring your ships into harbor, et cetera. But because they've been in place for so long, they provide an invaluable record of change. The technology we use now is a bit different. We'll use things like radar or sonar, but the principle is the same, is that you're measuring the height of the water relative to a point on land. So this is, you may have heard the term relative sea level rise. That's what we're talking about here. It's a measurement of the sea surface height relative to a point on land. And following my previous example, this is a taste of what the data look like. So I'm showing you observations from 2 tidal gauge records in southeastern New England, one from where I am in Woods Hole and one across the water in Nantucket. So what are we showing? So we have time going back a century on the x-axis, and we have height in meters along the y-axis. The orange data are the record from Woods Hole, and the blue from Nantucket. And what I'm doing here is I'm showing yearly averages. So I've smoothed out things like the seasons and tides and storm surges to really focus on the long-term change. And there's a few features of this graph that I want to point out. One is that, similar to previously, you have a general orientation of both of these curves that go from the bottom left to the top right. This is sea level rise. This is the sea level rise that we've seen in these 2 locations over the past century. It's on the order of about a foot of change over the past century at these 2 locations. This is actually much faster than what we saw over the late Holocene. If you remember, those were rates at about 1 millimeter per year or 4 inches per century. We're seeing triple that over the last century, okay? So the first thing is that we unambiguously see sea level rise at rates much faster than was observed during the late Holocene. So again, this idea that what we're seeing today is unique in a longer-term geological perspective. The second is that these curves, they're not sort of these smooth lines that are straight or that vary smoothly. They're kind of jagged. They sort of go up and down kind of noisily. They may be elevated or depressed for years or even decades at a time, deviating from that longer-term course of sea level rise. And this largely has to do with changes in local circulation and the weather, things like winds, pressure systems, river discharge, et cetera. So while there is this longer-term sea level rise signal, what we feel any given year or any given month can be quite different depending on local atmospheric and circulation conditions. 2 more things. One is that the blue line isn't as long as the orange line, and both of these lines feature gaps in them. And this is the reality of the data that we're working with, is that we don't have data records as long as we'd like. Some of them start more recently, and due to a variety of reasons, funding, instrumentation failure, is you can get data gaps and outages from time to time, and we have to deal with that. And the final thing, and this is maybe one of the most obvious things you'll see here, is that during periods of time when both time series exist, they look really, really similar. They both show very similar sea level rise signals from about 1970. Those yearly or decadal ups and downs look really, really similar between Nantucket and Woods Hole. That is, the long-term sea level change experience at Woods Hole is very similar to what's happening in Nantucket. So this is telling us that sea level rise is this process that unfolds over very large spatial scales. And what's experienced at one location can be very similar to what's experienced at another. But that's not to say that rates of sea level rise are constant. So here's sort of a zoom out plot. Before I was looking at changes at just 2 places, Nantucket and Woods Hole. Here's a nationwide image that I just published a couple of months ago in a paper. And what we're showing is the contiguous United States. All of the circles are the locations of long tidal gauge records, and the coloration indicates how much rise there's been over the past 125 years. And again, the graph here is in meters of change, so think meter, think ballpark, 3 feet of change, okay? And there's also a model estimate based on the data that is the more regular colored square values behind the colored circles where the tide gauges are. And what you see is, again, you don't see just one color. You see these really rich spatial patterns with, deep blues in some regions and deep reds in others and greens in some places. One thing I do want to point out is, if you remember that plot from the salt marsh data that I showed, where we had the highest rates on the mid-Atlantic coast, you see the signature of the same thing here, whereas if we restrict our view to the east coast, we see that in the Chesapeake Bay and Delaware River area, you see rates, you see circles that are a bit more orange, and if you move north or south of that, you get rates that are, colors that are more green. Okay, so that signature we saw in the salt marsh data also appears in the tide gauge data, and again, this is a reflection of long-term geological processes. Okay, there are also really interesting features, for example, along the Gulf of Mexico coast. We see these really, really deep reds, the fastest rates of change in places like southern Louisiana, and this reflects the fact that in that region you have a lot of what we call subsidence, or sinking of the land, which is due to a variety of reasons. There's been a lot of publicity around the practices of groundwater withdrawal in places like Texas, and oil and gas withdrawal in places like Louisiana, and how that creates an opportunity for the land to sink, thereby exacerbating rates of sea level rise that we experience for other reasons. So you get this rich pattern. Each of these locations has a story to tell about cause and effect. I don't have time to go into all of them, but suffice it to say that depending where you are in the US, you can experience very different rates of sea level rise. If we bring those all together, we see that in fact that sea level hasn't been rising at a constant rate, but in fact it's been accelerating. So what I've done here is, here's an estimate based on tide gauges that averages over the entire contiguous United States. So this is a time series by year, going from 1900 to the present. The y-axis, this RSL acronym, is the relative sea level idea that I mentioned before, so relative sea level. And again, this is a contiguous United States average. And what I'm trying to communicate here, and this is also published in a paper that I put out back in December, is that rates of sea level rise in the US have doubled over the past century. And you can see that by, if we look at this curve, it has the same signature that we've seen before, which is that the curve is oriented from the bottom left to the top right, but it's not a straight line. It features curvature such that it turns up more and more as you get to the present day, indicating that rates have doubled over the past century. And to try to illustrate that more, I've drawn this orange line on top of it, which is a curve fit or a quadratic fit, to those of you who have taken statistics. That illustrates the doubling of rise. So sea level is rising in the US. It happens at different rates in different places, as observed by tide gauges and paleoproxy records, and that over the past century, it's been accelerating. Okay. Now put that into context of the very first statement I said, which is that the 20th century saw the fastest rates in the past 3,000 years. So that recent century, which saw the fastest rates, itself also saw acceleration. So you kind of see this continual, the more and more you go to the present, the more and more sea level is accelerating and evidencing this unique behavior in a geological context. Well, why do we care? Well, one of the big reasons why, as talked about by Katie yesterday, is inundation and flooding. Okay, so the more you raise sea level, the more you reduce the freeboard between the height of the sea and coastal infrastructure, making it that much easier for very typical water level events to cause inundation. So I'm showing that data here for New London, because New London is one of only 3 locations in the state that features a long tidal gauge record. 2 graphs here. Again, as always, we have time running along the bottom. The top is the raw daily water level data from the New London tide gauge. That's what's shown in blue. And the units here are the feet above mean higher high water. That is the higher of the 2 daily high tides. Okay? The solid black line that runs from left to right, just under 2 feet above mean higher high water, this indicates the minor flooding threshold set by the National Weather Service. So whenever the daily highest water level exceeds that flood threshold, that identifies that you have a flooding event, evidenced by things like water in the street. Okay, and each of the orange dots identifies when you have one of these flooding events. Okay, and the flooding events are counted on the bottom. So the bar plot on the bottom simply count the number of the orange dots in the corresponding year above. And we see a clear trend with time. First of all, there have been floods in New London for a long time. If we look back earlier in time, we can see, for example, in 1954, this really high dot near 6 feet. This is the hurricane of 1954. So certainly there have been numerous flooding events in the area. As anyone who's lived in coastal New England knows, we get a lot of nor'easters, and along southern New England, we occasionally get hit with large hurricanes. But what I really want to point out is that I would argue you start to get this rapid increase in the number of nuisance floods in the recent decades. Why do I say that? Well, two reasons. One is that if you count these flooding events, you start to see much more systematic structure and elevation in the recent years in this bar plot. But also if we just look at how those orange dots, again, each one identifies a flooding event, if we look at how those orange dots cluster, okay? Yes, back in time you have these really dramatic events with very high water levels, but over the past couple of decades you see just these really dense clusters of orange circles that are just above that flooding threshold. So maybe these aren't the catastrophic, really rare events, but they're events that will cause you to have to take a different, if you're walking on the sidewalk and it's flooded, you've got to take a different way, or if you're driving to work. So these are these lower level nuisance floods. So we're seeing an increase in New London. Here are some more, I apologize for the really lousy quality of the figure here. These are some more regional and nationwide statistics. So the left is counting the number of flood days on average experienced in the Northeast over the past 3 decades. And you can see a clear increase. Again, it's not a smooth curve. There are jumps from year to year, just like we saw with the sea level data, but there's clearly this upward trajectory. And what we see on the left for the Northeast, we can compare that to the national average. The national average shows us that we've seen about a doubling in the rates of high tide flooding over the past 3 decades, but that here in the Northeast, we've seen an even higher increase. So that was a lot of slides about the sea level change we observe either through tidal gauges or paleoproxies. I want to talk a little bit more about process. I'm not going to spend a ton of time on things that I assume we all are pretty familiar with. So we know that if we're talking about global sea level rise, that comes about for 2 main reasons. One is that you melt ice on land. That melted ice becomes liquid water that runs into the ocean, increasing the mass and volume of the ocean, thereby causing global sea level rise. That's one. And the other is the ongoing warming of the ocean. So as some of you might know, the ocean has absorbed about 90% of the excess heat in the climate system due to climate change, and that's caused the oceans to warm and expand thermally. So those 2 factors, thermal expansion and the loss of land ice, are the main drivers of global mean sea level change. But as I've indicated, sea level rise doesn't happen evenly at the same rate everywhere, and there are spatial patterns to it. So I want to instead spend some time talking about some of the perhaps less familiar and less intuitive aspects of sea level change. Again, I'm reminded of Katie's figure showing all the Lego blocks and how she emphasized that if we're interested in flooding events, really it's a combination of processes. She talked about sea level rise and sea level anomalies and tides and waves and storm surge. There's a similar thing going on if we try to understand any of those components. So I'm focused mostly on the sea level rise part, and there are lots of processes in the Earth system that can give rise to sea level change. Again, we have the melting of land ice as illustrated by the cartoon glaciers to the left and the ice shelves here to the right. We have the warming of the ocean, but also changes in ocean circulation. We have changes in the land surface, which I'll talk more about, and changes in the hydrological cycle, things like El Nino, changing patterns of precipitation and evaporation. All of these things conspire to give the signature of sea level change in a particular region. And I want to take a few minutes to talk about ice. Okay, as I said before, we know that when we melt ice, we add mass to the ocean and we raise global sea level. But again, that doesn't happen evenly. And there are 2 main reasons why, and they come back to the idea that ice sheets are massive. Okay, and we're going to come back to our analogy of going to bed at night. So here's my cartoon of an ice sheet sitting on the solid Earth adjacent to an ocean. Okay, and the first thing that we want to say is that, as I've indicated by these arrows, is that ice sheets are so heavy and massive that they exert a force that depresses Earth's crust. So Earth's crust sinks beneath ice sheets. And not only that, the force of this ice sheet is so massive that not only does it depress the Earth's surface, is that it also affects change in the next layer down in Earth structure. It causes the movement of mantle material laterally outwards. So you have a sinking of land under the ice sheet, but you also have, you can see, does this work? I sort of illustrated with this little bump offshore that's created by the migration of the mantle material. Okay, so you get this deformation of the surface. The reverse happens when you melt an ice sheet. Okay, so when you melt an ice sheet, you release some of that pressure, so the Earth's surface is able to rebound. Okay, and that mantle material that was formerly evacuated laterally outward can return to the formerly glaciated center. And you get this motion here, where we have the former state indicated by the dashed lines and the new state indicated by the solid lines. So the first thing that ice sheets do is they cause deformation of the Earth. Why am I talking about this if I'm focused on sea level rise? Well, remember our definition of sea level, of relative sea level. It's the height of the sea you measure from a point on land. So if you're standing at the beach, you can feel sea level rise either if the tide rises or if the land you're standing on sinks with the ocean surface staying constant. So we care about both pieces. Okay? That's one part, the deformation of the shape of Earth. But we also change the gravity field. Remember, mass is the thing that determines gravitational attraction. Okay? And again, ice sheets are massive, so massive that they are able to exert a gravitational pull on the water nearby. So in a measurable way, the gravitational attraction of the ice sheets leads water to be slightly higher right adjacent to an ice sheet than it is farther away. So if we melt an ice sheet, we actually lose some of that gravitational attraction, okay? And counterintuitively, so we're melting an ice sheet, we're adding water to the ocean, but counterintuitively, when you do that, you dramatically reduce sea level around the ice sheet itself due to that gravitational attraction. And then as you move further offshore, you get more and more sea level rise. Okay, so you have these two principles of reshaping the Earth's surface and perturbing its gravitational field. And that leads to patterns like this. I'm going to show two maps of two different what we call fingerprints of sea level change due to ice sheets. So the first is sort of old ice. What I mean to say is this is the pattern of sea level change we expect due to the last ice age. So let me sort of orient you here. So we've got the globe. I'm showing all these colors to, in a relative sense, indicate sea level rise. So the bright yellows indicate rise, and the blues indicate fall. And I've used the black line to indicate the line of no motion. So this is the pattern of sea level rise, sea level change that we expect in the present day due to the melting of the former ice sheets, of the ice sheets that were present 10 or 20,000 years ago. Okay, let me explain some of these patterns here because this helps us interpret the data that we were looking at. So first is that we see these deep blues in formerly glaciated areas. So we see deep blue here in the Hudson Bay. This was the epicenter of the former Laurentide ice sheets. Why are we seeing deep blue indicating sea level fall? Because there's such fast rates of what we call rebound. The land itself is uplifting because it was formerly under the weight of that ice sheet. It's no longer there. So again, it's like getting out of bed and your mattress is resuming its former shape. Okay, so you get high rates of uplift, which feels like sea level fall along the coast. But the side effect of that is that you have this sort of yellow ringing pattern around that region, including portions of the mid-Atlantic US. This is where we have that, if you remember, the process we're imagining here causes this bulging of the land just around the periphery of the ice sheets that then sinks and subsides. So we see this elevated rate of sea level rise off the mid-Atlantic coast here due to those former ice sheets. And this is one of the big reasons why we see such fast rates of sea level rise in the mid-Atlantic compared to the southeast region and New England. This is the fingerprint of sea level change in the present day due to ancient ice. This is the fingerprint due to contemporary ice melt. Okay, so this is what we call the fingerprint of sea level change due to melting of the Greenland ice sheet. So we're imagining the loss of mass from the Greenland ice sheet. Again, we're using the colors to indicate relative rates of change, with blues indicating fall and yellow indicating rise. And we see in some ways a much simpler pattern here. We see these deep blues within a couple thousand miles of Greenland. This is that sea level fall that I was mentioning before. due primarily to the reduced gravitational attraction of the ice sheet. And then as we move farther and farther away, we get greater and greater rates of rise. So these are some of the ways that we can get spatial patterns of sea level change due to the processes that are contributing to them. I'll say one last word about observations and measurements. So sea level is complicated. It's hard to measure it just with tide gauges in the proxy record. So fortunately, over the past few decades, we have had new satellite technologies that have been orbiting Earth and giving us a much more detailed sea level rise picture. Not just sea level rise at the coast, but sea level rise globally. So I'll point out some of these. So here are some artist renditions of, this is what's called a radar altimeter. This is Sentinel-6, Michael Freilich, which was launched a few years ago, which measures the global sea level field every 10 days. This is a newer satellite called SWOT, or the Surface Water Ocean Topography Experiment, which has really revolutionized the field of sea level science. And this pair of satellites here is a mission known as GRACE, the Gravity Recovery and Climate Experiment. It doesn't measure sea level directly, but it measures those perturbations in the gravity field that I mentioned before due to the movement of mass on Earth's surface due to things like the melting of ice sheets. And with these kinds of measurements, we can put together these really, I think, beautiful pictures of how sea level is changing over the globe. So here's an image of, this is global sea level rise over the past 3 decades, as observed both by tidal gauges, that's what's shown as the little dots in some places along the coast, but also the color shading, which is everywhere over the ocean from satellites. So again, a few things to point out here. One, before I get into looking at the colors, which again are used to indicate rates of sea level rise in red or fall in blue, is that with tide gauges, we only had a partial view of sea level change, okay? But with the coming of satellites, it really represents this democratization of sea level data. We're able to have sea level information in parts of the world's coastline that we just didn't have any observations before. So this really changed the game in terms of sea level observations. So that's one piece. Another is that, again, you don't see a wash of a single color here. Yeah, you do see a lot more red than blue. This is that global sea level rise we keep mentioning. But it's not one color. You see some regions with these really deep saturated reds, some places where there's even some blue, and they can vary very dramatically over small distances like these alternations here in the Southern Ocean, or they can vary over much larger basin scales. For example, this gradation of colors here across the tropical Pacific Ocean. And a lot of these patterns have to do with something that I study a lot, which is the role of changing ocean circulation and currents. So you can tie a lot of these features that we see in the sea level rise field to contemporary changes in ocean circulation. So just to wrap that up, we have this amazing wealth of data on sea level rise, which has enabled us to better understand the multitude of processes in the solid Earth, in its ice sheets, in its oceans that cause sea level rise. And with that information, we can ask questions like, well, what next? Okay, so I'll spend a few slides talking about future projections of change, and then ongoing projects that I have in that vein. So coming back more locally to New London here, so what may the future look like here in New London? Here is a figure showing potential sea level futures. So we can't know the future with certainty. There are any number of sources of uncertainty, but we can bound it with an envelope. Okay, so here I'm showing time along the x-axis. We are going maybe 50 years into the past on the left, but going all the way to the year 2100 on the right, and we're showing feet of sea level rise on the y-axis relative to the year 2000. So the gray circles here are the same tide gauge data that I showed before, again, annual averages of the height of the seas. The black line is a simple quadratic fit to the data that's extrapolated forward into the future, and the different colors are the amount of sea level rise anticipated under different future scenarios that primarily relate to greenhouse gas concentrations in the atmosphere. And they range from futures where we have lower emissions, where we really curb greenhouse gas emissions, to more business as usual scenarios that are more on this high end. And for the middle orange curve, which is an intermediate scenario, I'm also showing a bound of uncertainty. Okay, so what we can see is that right now, all of the projections are pretty similar to that observation-based extrapolation. Another thing we notice is that over the next couple of years, there isn't really much difference between the scenarios. They all fall within a very, very narrow window for the next 20 to 30 years. It's not great news that sea level is rising, but this kind of information is actionable. We can say with high confidence that we know within a small envelope how much sea level will rise in a place like New London in the next 10, 20, 30 years. Things do start diverging quite radically once you get past the middle of the century, with this lower end scenario only implying about 1.5 feet of rise by end of century, to scenarios where you get more than 6 feet of rise. Okay? Why is this happening? So on the right, again, this is a nod to Katie's Lego plot. These are the drivers of change at 2050. Okay? So we've broken them down. So again, the height of each of these bars represents the relative contribution to change at that point in time. The green indicates vertical land motion, that is this sinking of the land that I mentioned before, localized here to New London. The various blue colors are the contributions of different bodies of ice, either the Antarctic ice sheet, the Greenland ice sheet, and also mountain glaciers worldwide. And it might surprise you to learn that mountain glaciers are comparable to the ice sheets. But the biggest bar here is this awful term, sterodynamic. What in the world is that? That's the combination of two things. That is the amount of what we call steric increase. That's the thermal expansion on average of the global oceans due to warming. So that's the stero part. And the dynamic part refers to ocean circulation changes. So due to a combination of the ocean warming, expanding, and its currents changing, we anticipate something like more than 0.5 foot of rise in New London by mid-century. One immediate consequence of that will be an increase in those high tide flooding events that I showed observations of before. So we know from the data that we're seeing an increase in high tide flooding here in New London, broadly along the Northeast, and nationwide. Again, the rates of high tide flooding have more than doubled in the US on average over the past 3 decades. And they're going to continue to rise in the future. So what we're able to do is, I liked the way that Katie described coming up with model experiments where she's able to roll Mother Nature's dice many, many times. So we're doing a similar exercise here where colleagues of mine have produced a probabilistic model that enables you to do similar dice rolls to, in a probabilistic sense, project how many high tide floods should be experienced in New London or any other location in the coming decades. So these are the number of floods that are predicted under that intermediate scenario. Remember, I had those 5 different colored curves in the previous plot. We're picking the middle of the road, 1, and looking at how many floods emerge. And what we see is that nowadays we're seeing something like 5 to 10 per year. But as we get to the end of this decade, we start to see this very sharp uptick, such that by the middle of the next decade, we're seeing about 24 days of flooding. And by mid-century, we're talking about 60 days of flooding on average per year. Okay? Important to know is that that's not going to fall evenly across the seasons due to the seasonality of sea level, the seasonality of tides, the fact that we get stronger storms in wintertime, for example, is that there's a clear seasonal distribution such that we're going to see more of those floods. This is for the year 2050. A lot of those floods are going to fall in the September, October, November time compared to other seasons. So these are the kinds of tools and applications that we're able to produce. I want to end with just a couple ongoing projects that I have at Woods Hole that are, so most of my time is devoted to doing the physical science of sea level rise, understanding the physical causes, what has caused past change, but you can't do this work and not be interested in some of the applications. So here are some of the things that I've been doing to try to further their use of sea level science for solutions and also training the next generation of scientists. So this is a project that we have ongoing to track coastal flooding. So both Katie and I have talked a lot about tidal gauges. These provide a very helpful quantitative picture of sea level rise. They're also the tool that we're using to track these increases in coastal floods. Now, if anyone has experienced high tide flooding, as you probably have, is you know that it's a very intermittent process spatially. I was talking to Derek last night about his very good fortune in parking near the Mystic Aquarium, and how there was a flooding event while he was away, and the rack line was just next to his car and did not get his car. That is to say that the flooding process and the impacts it causes vary strongly over very short distances. If you remember what I said earlier, that New London is one of 3 cities in the state that has a tide gauge. Flooding is a process that varies dramatically over short scales. We have 3 tidal gauges in the whole state. Those don't match up. We don't have an observing system now that is capable of, in a granular way, capturing this process. So what we're trying to do at Woods Hole, and we're certainly not the only ones trying to do this, we're trying to add to the body of community knowledge on this, is to create very low-cost sensors that can be put out en masse. You know, instead of having just 3 for a whole state, imagine having like a dozen of these in one town to track where it's flooding, why it's flooding, and when it's flooding in localities. So that's a project that's ongoing. But again, I think that tracking changes in coastal flooding isn't going to solve the problem. As I showed with the projections, we're going to see sea level rise through the century. And there's nothing magic about the year 2100. It's a convenient sort of time horizon that people use for projections. But for those of you who are more geologically minded, you know that sea level has a long memory. And we've already committed to centuries, if not millennia, of sea level rise, even if we stopped emitting CO2 today. Okay? So we do need to engage with policymakers. So one thing that I've been doing as an educator at Woods Hole Oceanographic is, so every fall I teach a seminar course on climate change. And I've been lucky a couple of years to have the opportunity that in conjunction with that class, I've been able to take a cohort of students to the United Nations Conference of the Parties, the climate change conference, both in Sharm el-Sheikh in Egypt, and more recently in Dubai and the United Arab Emirates. So here are a couple photographs of our presence in Dubai. So again, some of the students that I went with. And this was really a fantastic opportunity for them. The students we have coming through our program, which is primarily a physical and environmental science program, want to engage that science in application. And so this has been a really valuable way that we've been able to offer the students experience in that. And then finally, sea level is a hard physical science. It's mathematical, it's technical, and as I was telling folks at dinner last evening, surprisingly, given it being a hard physical science and it being so relevant and applicable, you're not going to find anywhere in this country or elsewhere a curriculum dedicated to the physical science of sea level change. So I've been heavily engaged in summer schools and other programs that try to provide a curriculum in sea level science to early career scientists. And most immediately, next month in Woods Hole, I'm hosting a 2-week summer school for PhD students that will cover all the basics of ocean physics and glacier physics and solid earth physics to try to, again, instead of the traditional way, which is you go to grad school, you're in a very narrow academic department and you learn part of the problem, to try to start students off as interdisciplinary from the beginning and provide that broad base of knowledge so that they're able to tackle these really complicated problems in sea level science. So a couple things that I hope to have communicated and what I'm looking to do going forward is that I hope you understand that sea level rise, it's a complex whole earth process and that we need input from experts in all those regions to help us understand. One of my big goals is to empower future generations of sea level scientists by providing them the experiences and the knowledge needed to tackle these problems, and also with other scientists to provide the data that can support stewardship and policy and adaptation. So thank you very much. I'm happy to take any questions. feel like you ask that question as if you've published in this area. Yeah, yeah. Just to repeat Peter's question, so it's on this theme of coastal sea level and ocean circulation. And some of you may be familiar with this idea of the global conveyor belt or the meridional overturning circulation. And in a separate sphere of climate science, there is consensus around the fact that in the coming century, due to ongoing warming, we will see a reduction of that circulation to the heat transport, which is responsible for maintaining the mild climate of Europe, which is partly why our European colleagues are so concerned about changes in the AMOC. But one of the long thought impacts of changes in the sorry, I said AMOC, that's the acronym, Atlantic Meridional Overturning Circulation. One of the long sort of concerning consequences of a decrease in the AMOC is an extra rise in sea level at the coast. This is something that we have seen consistently in climate models. As the overturning declines, you see an enhanced rise in sea level along the U.S. East Coast. There remains ongoing debates about whether we see the signature of that in observations, but from a purely ocean dynamical theoretical point of view, you do expect it. If you cease the production of deep water formation at high latitudes, which is the key process involved in the overturning, the equations of ocean physics do predict a substantial rise in sea level along the East Coast. The question, of course, is one, how much will the overturning weaken and will it collapse? Some of you might have seen sort of the news around it. There was actually a kind of a high profile paper that came out recently about changes in the Gulf Stream's latitude and whether that signals this upcoming collapse of the AMOC. So the questions are about what is the future trajectory of the AMOC? And if it does decline, how much sea level rise does that imply for the East Coast? It will imply some extra sea level rise. The precise amount, I think, remains to be determined. But from a purely theoretical point of view, you do expect it. Yep, so just to repeat, there were two questions embedded there. And one, I'm going to sort of retranslate as the pros and cons of, on the one hand, the tidal gauge measurements of the coast, and on the other hand, the satellite measurements. And then the second question was related to the inexpensive sensors that I talked about and what the motivation is there. So yes, so I think you're right to observe that each of these observing systems has different pros and cons. As I think I mentioned, these satellites perform, so the standard reference satellites that we use perform a repeat orbit of the entire globe every 10 days. That is, that every location that they monitor, they'll pass over that same spot once every 10 days. If you want to go and stand by the Thames River and just like watch how variable the river and the ocean offshore is, you'd say, well, taking one measurement every 10 days, that's not too great. So certainly the tide gauges have the advantage in that they're making measurements constantly, every minute or every 6 minutes or every hour. Okay, so that's one of the big pros of the tide gauges, that they've been in place for a long time and they make high frequency measurements. The downside, of course, is that they're only at the coast and that you tend to only have them in particular geographic regions, particularly the global north. Okay, so this is where the advantage of the satellites come in. Is yes, they make observations less frequently, but they make them on a much larger scale and over the global ocean. So one would think, well, why don't you combine both? Yes, people have tried to do that. So to take both observational systems and basically combine them to say, come up with some estimate of sea level change over the whole global ocean over the past century, kind of making it the best of both worlds. So you can do that kind of thing. It's not an either or, it can be a both and. And you're exactly right, your question about the sensors we're putting out. There's no problem per se with tidal gauges. They're extremely accurate. And they do the job that they were developed to do. The issue is that given this new use that we're seeing for that kind of technology, the density of the instruments isn't nearly enough. Okay, so the goal is, how do we get more instruments out, and how can we do that cheaply? The gauges that people like the National Oceanic and Atmospheric Administration put out, that, for example, Katie talked about, these are sort of the gold standard. They cost a lot of money. Most municipalities couldn't afford to have one on their, as a line item in their budget, right? So that really motivates us to say, well, what can we do? What's the trade-off between measuring the thing that we're interested in, but doing it in an inexpensive enough way that is more affordable? So right now, for example, we're using off-the-shelf parts. It costs maybe $200 or $300 to make one of these things. So we're having that as an alternative to the longer NOAA gauges. So just to wrap this up, the NOAA gauges, gold standard, they'll give you the long-term sea level rise picture. They're really concerned with things like vertical stability, whereas ours, we're not trying to measure sea level rise so much, but trying to get the geography of flooding. Yeah, I'll give sort of three examples. See if I can remember the three examples I just thought of. One is that, on Cape Cod, for example, you see such variation from town to town in terms of where that town is at, in terms of coming up with coastal resiliency plans or having dedicated staff on the municipal level that devote their time to this issue. So for example, a place like Nantucket has a devoted coastal resilience officer who's really making a lot of headway trying to get more observations in a place like Nantucket. Nantucket is a place that actually, more than most in Massachusetts, sees this high tide flooding issue because so much of its infrastructure is low elevation. In a place like Falmouth, where I am, so Woods Hole is a village in Falmouth, we have just over the past year hired a coastal resilience officer at the town level, and I've been talking with him. He, for example, has taken some of the figures I've produced, and he has like one of the pages on the town website, so he's got that graph up there. So one is that you see different towns and municipalities being at different stages of sort of funding people to tackle these issues, because if you don't have sort of a point person or a champion, it's just really difficult. The second thing is talking about organizations like Sea Grant, who will be, I understand, here today, the Connecticut Sea Grant, which is a fabulous organization whose job it is to be that middle person to sort of translate and sort of mediate conversation between scientists and practitioners. So I've been working a lot with the folks at Hui Sea Grant, and the hope is to kind of relate your question to the things I just showed is on the cusp of getting some funding to try to really get these instruments out all over Cape Cod, which would be phenomenal. The second is that it can also vary state by state. So I'm involved as a chapter author in the upcoming, I'm leading the chapter on sea level rise for the Massachusetts State Climate Change Report. So that's been a really interesting avenue to be able to not only write about sea level change in Massachusetts for the state, but also to have a view onto what the state's priorities and needs are in terms of that data. So, but again, it's frustratingly like ad hoc and sort of case by case, and is contingent on what infrastructure and sort of people power is in place in a particular place, and that could look very different in Connecticut. I don't know, but trying to use my position at Hui to try to make these connections to try to get that data out there to receptive audiences. Thank you.
Thank you. That was such an awesome start to the day. We're just a little bit behind time. That's okay. We're gonna take time for like 15-minute break or so. We should have some coffee and refreshments back up behind. Maybe if everybody could plan to kind of migrate back in about 5 past, we'll get started with the next talk in just a few. Thanks. All right, welcome back, everybody. We're gonna get started with the second session of the day. I wanted to mention, I'm gonna see if I can find this. We have for Q&A, I forgot, I lost track of this during the first session, but we do have the coolest thing. We have a ball with a microphone in it that we could pass around for anyone who has a question to ask. So we'll see if we, oh, it is. Oh, thank you, we got it, yeah. So we might try to use that in this next session. Okay, I'd like to introduce our next student who will introduce the next speaker. Really excited to invite Annie Toms up to the podium here. Annie is one of our seniors in the Goodwin-Niering Center for the Environment, a double major in biology and education, right? Oh, education minor, I'm sorry, education minor. Annie is our specialist in environmental education, and her senior project this year is focusing on invasive species management at a site here in New London called Bates Woods. So, Annie, welcome. Yeah.
Thank you, Professor Toda. As he said, my name's Annie and I'm a senior here. And I have the pleasure of introducing our next speaker, Tammy Lewis. Tammy earned her bachelor's from Vassar College before earning her PhD from the University of California, Davis. Currently, she's a professor of environmental sociology at the City University of New York. She has always had an interest in transnational social movements and has conducted research in a wide variety of places, including Ecuador, where she conducted research as a Fulbright scholar. She also recently just got back from a research trip in California, so we're really grateful you could make it. She has received many awards, including awards for excellence in both mentorship and research. She was also elected and served as the chair of the environmental sociology section of the American Sociological Association. She has many publications, including 20 Lessons in Environmental Sociology and Green Gentrification, Urban Sustainability, and the Struggle for Environmental Justice, which I've had the great pleasure to read in class here at GON. It is my honor to welcome Tammy Lewis to give her a lecture titled Climate Disasters in New York City, Assessing 4 Post-Sandy Public Investment Strategies.
Thanks, Annie. I want to start off by thanking the organizers of the symposium. I've already learned so much in the 2 talks that we've heard and in the conversations at dinner and in our breaks today. I especially want to thank my colleague from sociology, Dr. Julia Flagg, who invited me here as part of the planning program. And I also want to thank my collaborator in the research that I'm going to present today, Dr. Kenneth Gould. I've been having conversations today with people about interdisciplinary studies. I am trained as a sociologist, and I come to issues about the environment from a sociological lens. But we're living in a period of crisis where we have rising inequality, and we're coming to the end of an era of climate stability, and it really forces us to see that we as academics can't answer the problems that we face from any single discipline. We really need to do this as a team. And I think the center is really kind of like a shining piece of that at Connecticut College that is training students to think interdisciplinarily. And so it's really great to see that education going on at Connecticut College. So today I'm going to talk about my version of sea level rise through the lens of a sociologist. And I'm going to look at sea level rise in terms of justice and who wins and who loses with sea level rise, and how changes to the environment and our social responses to them exacerbate, reproduce, and in some very rare cases, ameliorate inequality. So thank you for making this nice slide for my lecture, Kelly. Okay, so here's the title of my talk that Annie gave you. So let me start out by setting the stage, the kind of broad context. we see a socio-ecological paradox on the coast. And on the one side, we have people moving to the coast. And so from 1970 to 2010, we have an increase in coastal counties in the US of 40%. And if we look at this globally, 2 out of 3 megacities are located on the coast. We heard this in our lecture last night as well from Katie. Now, at the same time people are moving to the coast, we have intensifying storms at the coast, and we have sea level rise. The Intergovernmental Panel on Climate Change predicts that the risks will increase over time. And we heard from our last speaker, we saw the data, we saw why. I'm going to do a really quick look at some of the trends, which are just going to reinforce what Chris showed to me. And let me just tell you, I am a sociologist, so I borrow all these slides from my scientist friends, right? And so we know that atmospheric carbon dioxide is rising, and this is resulting in hotter landmass and hotter oceans and in sea level rise, right? So I'm just kind of stating what we already have heard, right? The natural scientists are laying down this information for the social sciences. Now, what does this mean for me? What does this mean for our people living on the urban coast? I'm going to talk to you today about New York City. And New York City in the aftermath of Superstorm Sandy is the context of our research. Anybody know where I took this picture from? Top of the World Trade Center, right? So I think this picture is interesting because New York City is really a city of water. I don't know that that's how we think of it, but we are surrounded by water. There's 8 million people in New York City, and 400,000 live in the 1% flood zone. If you were at the talk last night, you know that the 1% flood zone is the chance, let me see if I can get this right, scientists, the chance that a 100-year flood will happen in a given geographical area. So by 21,000, 2.2 million people are predicted to live in the flood zone. And that is not just because we have sea level rise, it's actually because people are moving into the flood zone. In the 10 years since Hurricane Sandy, New York State real estate values in the flood zone increased by 44%. These are desirable places to live. And so I'm going to talk to you today about New York City as an example of the global change paradox, that the human population is increasingly moving into harm's way on the precarious coast. I feel like I don't need to explain this at all because Chris just explained it all to you. So we have sea level rise in New York City, but it's happening faster than in many other places. I'm not going to say more than that. If there are any questions at the end, they'll go to Chris. This is a map that shows the 100-year flood zone level. And I know it's kind of hard to see, but what I want you to see is that it keeps getting bigger, the flood zone area. So more and more of New York City is being covered by this area. This map was generated in 2009 before Sandy hit. Red was before Sandy, purple is the current estimate, the orange is by the year 2050, and yellow by 2100. And the areas that are vulnerable to storm surge are even more extensive. Let me point out some areas here. Okay. So we have the Hudson River right here. We have the Upper Bay. We have, this is Jamaica Bay, Lower Bay. This is the Atlantic Ocean. And these are areas that I'm going to be talking about as we continue. A little more context. Again, thank you, Chris. We have sunny day flooding in New York City. You might think of, Miami, which is often hyped in the news as being a site of sunny day flooding, but we have this in New York City. I actually took this photo from the subway, right? So this is the A train, which actually runs the whole length of New York City, but this is in the south, in Queens, in the Rockaway area. Sunny day flooding might not seem like such a big deal, but if you have kids who have to get to school, if you need to get to work, if you have an emergency, it becomes a very big deal. And sunny day flooding in this area is a result of sea level rise. And one of the points I wanted to make with this slide is just to say climate change isn't something we're waiting for and getting ready for. It is already here. So, what am I going to talk about today? Here's my basic argument. Using New York City as a case study, I want to show you that we really find ourselves at a moment of crisis, but it's also a moment of opportunity. So sea level rise and storm threats, we know, are already threatening coasts. And so we need to make decisions now that are going to impact the future human habitability of the coast for centuries to come, especially with climate disasters. Now, public policy shapes the development paths and the equity outcomes that we are going to see. And the decisions we make today, in some ways, lock in future investments. And so, if you only take one thing away from today's talk, it is that I want you to think about how the policy choices we make today are going to direct our future one way or another. Okay. So Hurricane Sandy was really a tipping point in New York City in terms of thinking about planning and thinking about policy. At this point, the US had already had 2 major storms in recent time that had hit 2 major cities. We had Hurricane Katrina in 2005 and then Hurricane Sandy in 2012. In New York City, we lost communication, power, transportation, and infrastructure. Was anybody here in New York City at that time? Yeah, so you lived through it, and really depended on where you live, right? If you lived in Rockaway versus Lower East Side versus the Bronx. So when Sandy hit New York City, it was actually not a hurricane anymore. That's why we call it a superstorm. But what it did do, it pushed a lot of water onto shore and into the New York Harbor. And that New York Harbor part, where it comes together with New Jersey, it's called the Bight. And it's a bight because it's scrunching the water together, right? So it really creates a high wave. So Superstorm Sandy was what triggered adaptation planning in New York City. And I should just say something about the theme of the conference, right? So we're looking at these 3 themes. Mine's really this last slide here, right? How we adapt as human beings. So the neighborhood level impact of Sandy depended on environmental factors like elevation and proximity to the shore. It also depended on socioeconomic factors like race, class, age, and disability status. People died, homes were damaged and destroyed, and the flooding cost the city billions of dollars. This is actually the Rockaway Boardwalk, which used to be made of boards. It no longer is, and I'll talk about that in a few minutes. So why does public policy matter? So we look at how the government responded to this enormous disaster, and this matters because governments are key responders to disasters, and the decisions they make have long-term impacts. And in these cases of the government responding to disasters, there's a lot of demands for quick recovery, right? People want things to be the way they were the day before the storm, right? So there can be some really knee-jerk reactions of just, let's put everything back together. You might remember Chris Christie saying, we're stronger than the storm, right? Somehow that like human beings could easily overcome this. And politicians want to reduce stress, right? People have lost family members, they've lost property, and they're in a a period of upset. But the choices that we make really require some reflection, some long-term planning, and considerations of the long-term implications in terms of both expenditures and in terms of the equity outcomes. Who's being helped, who's being left behind. So how could we respond? This is a nice little schematic done by A.R. Siders, who's at the Disaster Research Center at University of Delaware, who does wonderful work on this. There's a lot of strategies we could use, and the leading strategies fall under the rubric of protect, or in this schema, resist, accommodate, and retreat. Governments could also just do nothing, right? They could respond with no response. They could let just nature and markets work things out, simply leaving the coast as it is and allow for continued flooding. Governments could also resist, and resist often requires massive coastal engineering. People call this shoreline armoring. And this is a major public expense, and something that I think is really interesting, and you can see here, is where we resist, what happens to the beach? Mostly it disappears, right? So when you choose to armor, there's no more beach. A third thing we could do is to accommodate flooding, right? So here you see structural mitigation, meaning that we've changed the structures so that they can accommodate flooding. So governments could use building codes to require that buildings be elevated and other structural things take place. And then the final thing we could do is retreat. This last category is sometimes called managed retreat. Governments could coordinate the movement of people and homes out of harm's way from rising waters through publicly funded buyouts. So these are the four kind of ideal types, if you will, of policies that government could take. And so what my colleague and I do then is try to find examples of these four cases after Superstorm Sandy to see what happens when these strategies are applied and who benefits and who loses. So let me tell you a little bit about the cases we're going to look at. So Manhattan is up here, okay? We're not going to talk about Manhattan. That's what most people think of when you think of New York City. We're not talking about that today. This is Staten Island. This is Brooklyn. Rockaway Beach and Edgemere and Broad Channel, these are all in Queens. If you've ever ridden the A train down to Queens, it runs right here through Broad Channel. The picture I showed you of sunny day flooding was taken from around here. So in each of these four neighborhoods, a different policy was used. And so now I'm going to talk specifically about these cases. Okay, this is Edgemere, Queens, and I want you to take note of the housing stock in these kinds of pictures. And in Edgemere, Queens, it was essentially a do-nothing policy. And if you think about a neoliberal political economy, leaving disaster recovery to market forces without government intervention is an option, and that is primarily what happened here. And in this type of case, the problem of climate precarity is left to private actors to address on their own. So that would be homeowners, renters, insurance companies, and real estate developers. And so the ability to recover in place then depends on family finances, insurance policy payouts, the availability of insurance, and real estate values, assessments, and markets. And it very much depends on the ability of individual households to access these options. And so people with limited finances are really in a tough situation in that they're either forced to sell their damaged property or to abandon damaged properties. And residents with more money have more options, right? They could choose to rebuild or do something else. Now, Edgemere, I'm going to give you a little background and just going to highlight something on this slide that for all these slides, what I've given you is the statistics for the specific place, and then the numbers in red are the averages for all of New York City, so you can get a sense of what these neighborhoods are like. You can see here, Edgemere is predominantly black, pretty poor, and has a low number of owner-occupied housing units. Also, you should note that New York City in general has a very low rate of home ownership. So it's about 1 in 3 people actually own homes. So in poor communities like Edgemere, where residents had limited access to post-disaster policy interventions and limited resources, they also had low social capital, and the result for them was like a do-nothing scenario. Now, Edgemere, Queens is really far from the center of the Manhattan universe, right? It's in a remote coastal corner of New York City, and there's been intergenerational poverty in this area and limited political power. The housing stock is a mix of these little bungalows and then also high-rises with apartments and also public housing. Now, following Sandy, there were policy interventions to support and repair rebuilding, but because of the limited individual and community power, which was also coupled with a very highly bureaucratic process to be able to access funds, very few people in Edgemere got these funds. And so these people were really left to absorb the economic losses. And this is really tough in a community that's 42% below the poverty line. And another important thing here to think about is that when you have only 13% of people who are living in a house that they own, most of these people are renters. So people who rented in this area were dependent really on their landlords to be able to do something for them. I don't know how many of you, read the New York Times, and there's been follow-up stories about people in Edgemere, and you still have people who are renters in Edgemere who are living in horribly molded homes, and they lived in damaged housing for years, and many simply left. So this was Sandy in Edgemere, and then what happened after Sandy? So some residents took their losses and relocated. They abandoned their homes and they abandoned their rentals. Oftentimes, when there are climate disasters, areas that were poor are replaced with wealthier newcomers. The costs of insurance are incredibly high, and so the recovery in terms of housing skews toward wealthy, and many of you may have heard of the term climate gentrification. This is a form of it. Other kinds of climate gentrification are when people from the coast move to higher areas that are less expensive, but this is another form of it, and we can discuss that in the Q&A. So after Hurricane Sandy in 2022, the family poverty rate was down to 25% from 42%. Largely because poor people moved out and a new housing development attracted buyers with higher income. And there are now more housing units in Edgemere than there were prior to Sandy, and slightly more people, right? So, at the beginning when I talked about more people moving into flood zone 1, here you see it in a neighborhood case. So this is the example of what happens when you do nothing. The next case I want to talk about is managed retreat. And the case I'm going to talk about is Oakwood Beach, which is in Staten Island. So as I said before, managed retreat is the purposeful, coordinated movement of people and assets out of harm's way. There are so many obstacles to managed retreat, and it begins with the actual term. People don't like the idea of retreat because it implies somehow they are losing, right? And so some people have suggested we use other terms such as strategic relocation, managed realignment, or transformative adaptation. In theory, managed retreat could be a proactive strategy to move people away from potential danger, but in practice in the US, it's been very reactive. So we don't really deal with moving people away until a disaster has occurred. So it's also a really hard sell. Politicians really don't want to move people out of their district. They want to keep people living in their district because they're paying taxes. And most communities really prefer to stay together, and there's a strong sense in some neighborhoods of place attachment. Another reason managed retreat is hard is because it's quite costly. The public costs are high, and it's also jurisdictionally quite difficult, right? Who should be in charge of this? Who should be paying? In New York City, and this is true elsewhere as well, finding affordable places to live is also difficult. Some research has shown that people who move in these situations actually move to places that are worse off in terms of flooding. And then there's equity concerns. Who gets bought out and who does not? A recent study found that Black populations are less likely to receive buyouts, and when they do, the money they receive is less than in white communities. The upside is in communities where this has happened, it has increased shoreline resilience and has created open space for recreation. And so in this picture here, you just see, I know you can't see it really well, but these are calls for the governor to please buy out community in Oakwood Beach. This is after the storm, and that's actually what happened. So Oakwood Beach is in Staten Island, which is the least densely populated borough. And this particular community had witnessed storm after storm after storm. There was intergenerational flooding. People were kind of done with this. This area was also one of the places that was hardest hit by Sandy. They received a storm surge of 16 feet. And of the immediate deaths that happened in the city, 24 of them were here. So they really felt the effects of the storm. So this particular community was open to buyouts and relocation, but they were very adamant that they wanted the land to be returned to nature and not to be redeveloped because they didn't want to see another community have to go through what they had gone through. Now, you should note here that there's a really big difference in this community, a couple really big differences. First of all, it's a mostly white community. It has a low poverty rate and a really high percentage of owner-occupied homes, right? So these are people who lived in these homes, they grew up in these homes, their parents passed the homes down to them, so they had both place attachment, they had also community, and they had collective memory. So in this area, 504 homeowners received pre-storm fair market values for their houses. This cost $203 million. They also received incentives of 10% of their housing value if they remained in the state, and they received another 5% incentive to remain in Staten Island. That's kind of how we appeased the politicians to keep their taxpayers. And the plan is to keep this area as open space, but is a little complicated, which I could perhaps get into in the question and answer period. So what does this look like now, years later? Well, in Oakwood Beach, it's the only one of the 4 neighborhoods that I'm going to talk about that lost housing units, right? So the number of places to live there declined, and also lost population. So coastal precarity has been radically reduced because people and assets in Oakwood Beach are no longer in harm's way. Third case. Okay, so that's what happened when the state bought houses out. Now we're going to look at structural mitigation when the state's policy is to change building permits, structural accommodation. So this is Broad Channel, Queens. It's this little spit here in the middle of Jamaica Bay. It's very narrow. There's one street that goes down the middle with basically a block on either side. You can see the picture here. These are actually post-Sandy houses. But with structural mitigation, governments can require communities to accommodate to rising sea level by creating more stringent building codes and zoning regulations. And this typically requires structures to be either set back from a water source or in these cases raised up. Sometimes it requires that electrical systems and whatnot be put on a roof instead of a basement. And these practices strengthen structures to withstand water and wind. And you could see how with these raised structures, water could run through the bottom of these buildings and not necessarily damage the living structure. This is what's called wet flood proofing. And I think maybe we have somebody from FEMA here, dry flood proofing, thank you, who I hope can help with some of our Q&A later too. And so these practices lower the flood vulnerability of residential and commercial buildings. And the National Flood Insurance Program promotes structural mitigation and accommodation through their post-disaster funding. And through this funding, homeowners have to comply with raising their home to a certain floodplain level, and it's dependent on what the base flood elevation is. In New York City, homeowners had to raise their house between 10 and 14 feet. So in New York City, this was used mostly in Queens and can be seen in neighborhoods that were surrounded by water like Broad Channel. In this particular case, the money was not available prior to Sandy, but it was available after Sandy, and that's something I think we should talk about in thinking about solutions. And complying with structural mitigation requirements raises the cost of maintaining a home, and it is a greater burden for poorer families. So if we look at Broad Channel, you'll see that there's a lot of similarities with the demographics as those of Oakwood Beach. So you have a predominantly white neighborhood with low poverty rate, and again, a high percentage of home ownership. So this gave the people in this area a lot of agency in terms of what they decided to do. So the city program helped 12,500 families recover, homeowners recover, and in Broad Channel, they elevated 250 buildings that were inundated during Sandy. What we see after Sandy in Broad Channel is that the population decreased slightly and the number of housing units increased slightly. So not all the families had the funds to be able to do this work, and as I noted before, renters have less control over these kind of improvements. And so the structural mitigation strategy really favors home ownership. It's going to benefit people who can do something to their house. And in sociological terms, we would say this is a private solution to a public problem. And it really exacerbates inequality, right, by leaving it up to the individual homeowner. And we make the argument that upfront grants would be a much more effective way to deal with this, so being more proactive in helping people with their homes. And so in this picture here, you can see that those who can afford to elevate their homes and those who can't, we're seeing they're moving out. I mean, this picture just happens to illustrate that perfectly. And so when the next storm comes, you have to ask what's going to happen to the new homeowner in this house that is not elevated. All right, so that is the case when the state says, we're going to change the codes so that where you live is safer. All right, final case here, massive coastal reconstruction. So this is resisting. This is armoring the coast. And this is a really common response to coastal climate disasters. You see this in global megacities around the world, where we're using hard engineering solutions to hold back the water, right? We think we can hold back the sea. You see this in the construction of harbor-wide sea gates, barriers, dikes, berms, groins, artificial dunes. These are becoming more and more of a standard approach to protect real estate that's on the beaches, to protect infrastructure, and to protect people from rising sea levels. The high cost of these plans is justified by saying that we are protecting real estate, right? We're protecting everything that we've already built. And in many ways of these various strategies, the coastal engineering offers or requires the least social change, right? We're basically saying, you don't need to change anything. We're just going to build this wall. We're not going to cede any land to the ocean. So the case we're looking at here is Rockaway Beach. Rock, rock, Rockaway Beach. You guys know the song by the Ramones. This is the Rockaway Beach. And Rockaway Beach is a diverse linear community. It's a thin peninsula between the bay and the ocean, and it hosts millions of beachgoers every year. Anyone ever been at Rockaway Beach? Yes. Rockaway Beach is a great place to go. It's the longest beach in New York City, and it's where New York City faces the Atlantic Ocean. And after Sandy, Mayor Bloomberg basically came out and said, you know, we are going to rebuild the boardwalk. It was his version of Chris Christie's, you know, Stronger Than the Storm. And so the boardwalk was totally wiped out during Hurricane Sandy, and he decided, we're going to put this back. It's going to be a sign of our resilience. And so it was one of the first things that were actually erected back in Rockaway, and they set up 2 little spots where there were concessions so people could like go to the beach, you know, get an ice cream cone and feel like things were normal again. So after Sandy, instead of rebuilding with a wooden boardwalk, what they did was they built a concrete boardwalk, which was essentially armoring the beach, right? So there was a concrete boardwalk that is built, still is there, and then they put dunes in front of the boardwalk, and this cost approximately $385 million. So this was great. Everyone was happy they could go back to the beach. And it was also not as bad as the ideal type I showed you where the beach disappeared, because they also built artificial dunes, right? And so like if you have houses here, you have the boardwalk here, you have artificial dunes, and then you have the beach. And so it was smart in that it preserved the beach, because that is the economic engine for this area, right? So it couldn't, the city really couldn't afford to be getting rid of the beach. Then what happened was 8 years after Sandy, we embarked on what is called the Atlantic Coastal Resilience Project. And that was an additional $400 million. And that was because this beach was not going to stay in place. It was not, the original boardwalk was not built to the sea level rise that we were seeing. And this also included 18 groins, which you can see up here. So about every block you have one of those. What those do is actually hold the sand in place, right? So when we also had sand replenishment, right? So that we would be able to continue going to the beach. And so you have this original $385 million project that was thought to be good enough. And then just 3 years after that, they started this new project, which is $400 million. This is still being built. These pictures were taken 2 summers ago. It's still under construction. So after Sandy, what we see in Rockaway Beach is we see incredible growth in population and densification. And we have a 10% increase of people living there and a 3% increase in the housing units. I think that 3% increase is an undercount. The data that we're using is from 2022, and I would say from 2022 to 2026, there's been at least 4 more high-rises built in that time. So I think that the intensification is happening even more. And so we have problems with this because the engineering that's being used is not, well, first of all, it's very expensive, but it's also not keeping pace with the actual acceleration of the sea level rise. And the other thing that folks are saying is that it's strong immediately upon completion, but over time it weakens with age. And so we have some issues with the engineering piece, and this particular piece of engineering is interesting because it's hard engineering and nature-based engineering, and hopefully we'll have time to talk about that too, because you're using the hard concrete, but then you're also using the constructed dunes, which give you the visual of everything's beautiful and nice there. In terms of equity outcomes, we see this as a public solution to a public problem. And in that, it's protecting everyone who is beyond the wall, right? So it doesn't matter if you're a renter or an owner in this situation, you're being somewhat protected. So your household income is not a factor. So it ostensibly protects everyone. So this is what happens when the government spends a lot of your taxpayer money, right? This is not necessarily coming from New York State, it's coming from the US Army Corps. So now I want to quickly go through 4 major takeaways about the policies for this. And the first one is with regard to population density. And what we found with these 4 different policies was that the only significant reduction of movement toward the coast came with managed retreat. That's the only strategy that significantly decreased the number of people living in flood zone 1 and the number of housing units. Seems pretty obvious, but that is, you know, if we want to move people away, managed retreat is a good strategy. And in the other 3 policy types, we saw increase in the number of houses and increase in the number of people living in vulnerable areas. So if we're looking at how these policies affect the movement toward the coast, managed retreat seems to be the one that makes most ecological sense. The second point I want to make is about class inequality. And what we found in these cases that when there were household level solutions, they really benefited people with wealth. So if we look at Broad Channel and if we look at Oakwood Beach, the people who had the means to repair their house or the means to organize really had the most choices and were left, had most access to these policies. We also found, that renters obviously had the least choice. They were the ones who were most dependent on the landlords and other people to be able to kind of get their lives back together. We also found that the massive coastal reconstruction protected everyone, but at a very high cost, and also with the unecological outcomes of enabling people to move back to the coast. The third piece, and I want to go back to Rockaway for this, and so I noted that the first round was $385 billion to do this, and now we put the second $357 million in it. There were only 3-year gap between these two things. So like, what's going to happen in the next 3 years? We really don't know. So there's a lot of cost around the most massive coastal reconstruction, but there's also a lot of uncertainty. And I think, Chris's talk really showed us that, well, he showed us there's uncertainty, but there's a band of certainty, but we don't know if we're going to be on that high band or that low band. And that makes a difference when every centimeter more that you're building the wall has significant costs. And then the last kind of lesson here is about development lock-in. And it's just ironic that the strategy to resist is enabling more people to move into flood zone 1. So we have private capital feeling like they can invest in this zone because the state is protecting this zone. This picture, it's a little hard to see, but let me try to orient you. The ocean is over there, and this is taken from the boardwalk, right? So this is one of those condo buildings I was telling you about. So what used to be here is a single-family home. It was a large single-family home. And developer bought it and now is putting in a condo that's going to have 52 units, right? So they feel safe in doing this because they have this nice boardwalk and all the other protection from the dunes. And so what we get here then is this cycle of perverse public and private investment. So we have this feedback loop, which we argue is anti-ecological, right? So what we're doing socially is actually putting money into areas that are going to protect developer spaces, and then developers are putting money into this space and more people are moving there, and then it makes the justification for putting the wall higher because there's more real estate value here, and it keeps going on and on. And so we basically see that the ecosystem logic here is really being trumped by the political economy. During the break, Julia and I, and a botanist, we're talking about how great Chris's talk was and how great the data are. Like, we know what's happening with sea level rise, right? We're not like, oh, is it going up? Is it going down? We know, right? And we know in New York State it's going faster. But what we really don't know from the social science side is what we should be doing about this, right? So what's our best approach to deal with humans who want to live by the coast? What's our best approach to deal with humans who already are living by the coast? Cities all around the world are dealing with this. We are not alone. Currently, 2.15 billion people live in the near coastal zone. 898 million people live in the low elevation coastal zone globally. This is a major proportion of our societies. I know this is really small and you probably can't see it, but currently in the US, we have 3.5 million people currently exposed in New York and Miami alone, with predictions rising to 8 million in 2070. We have $540 billion in assets presently in those zones and rising. So this is a problem that's not going away. It's going to get worse. I was also saying to Julia, I think we need to have the chaplain back to talk about hope and action at the end of this conference, because I don't have good news for you. And finally, I just want to kind of broaden out and show you a couple examples from other places. This is the Delta Works in Zeeland, in the Netherlands. The Netherlands are the experts in the engineering around this. They've been doing this a long time. They live at sea level. They've been holding the water out. But this, in the late 20th century, cost $13 billion for them to build. And they now need to re-engineer it based on sea level rise, and every centimeter of sea level rise causes millions, if not billions of dollars of needed protection. Other places are doing this as well. Houston is looking at constructing a sea gate following the 2008 hurricane that devastated Galveston. It's currently estimated to take 20 years and cost $57 billion. That's current predictions. Lagos is building a giant seawall and moving large numbers of people into flood zone 1. Jakarta is building a giant seawall similarly and moving people into that area. So armoring the coast is happening in many cities around the world, and the capital commitment to armor these cities is huge. And some of us this last week might have been thinking about funding and choices that we make. We're spending $1 billion a day in Iran. What if we were spending $1 billion a day dealing with this problem? But we're going to have this going on around the world. We're going to be spending billions of dollars on this instead of, say, on education and other things. And so it really becomes a value question for societies of how we want to choose to spend our dollars. So in New York City, we have a plan, the New York Harbor Seagate system. The estimate for this is $57 billion. They're already building part of this on the Lower East Side. I didn't have a chance to take a picture, but on the Lower East Side right now, if you ride your bike on the bike path, there is a seawall to your right. You cannot actually see the water anymore in some parts of those parts of New York. So sealing off the cities, basically making them islands, is really expensive. And ultimately, major urban areas are going to retreat from the sea, but from what we see so far, we think that it's unlikely that it's going to be managed or voluntary. So this is a problem for planners in a big way. We have a housing crisis, we have sea level rise. It's expensive, so what are we gonna do? I do not have answers for you. And I certainly hope that in this afternoon's panel that we're gonna be having time to engage in this, because it's not simply a scientific question. And there are political stakes in this. I don't think it's a question that of us all just getting together and being educated and making some decision, because as a sociologist, I see this as related to power, who has power, who can make decisions, who has the funding to do these things, and so forth. So thank you. Do you get to throw that around?
So thank you so much, Tammy. Lunch is coming up next. We have this amazing thing. We have this microphone ball that we'll use. So we could take 7, 8, maybe 10 minutes for questions before lunch. Yeah, thanks.
I was going to chuck it.
Can you?
It is light.
Not sure exactly what to do with this thing, but okay. That was so wonderful. Thank you so much for all of that. So I taught the seminar for the Goodwin-Niering Center students in the fall, and they know I'm very much against the armoring aspect and so forth. And it seems to be a fairly logical kind of idea to just move people away from the coast. But there's other hazards that climate change pose, and I'm curious about your thoughts on this. One of them, of course, is temperature extremes, right? And so we've got continentality in much of the United States where high temperatures are going to be more extreme in the interior, and so that's going to push everyone to the coast because the coastline has a moderating effect. So you've got these kind of dual hazards that are pushing people in different directions, right? And there's no good place that we can land, basically. So I'm curious what your thoughts are about that other thing that are actually pushing people to the coastline.
That's a great question. And I think if we look at the history of Rockaway and the history of Oakwood Beach, it may provide some answers to that. Both of these communities did not used to be residential. And so what they were basically bungalow colonies that people who lived in the hot cities, you know, think like 1920s, no air conditioning, smelly, stinky, crowded. But what they would do is families would go down to their bungalows in the summer when it was hot. And these bungalows were not very strong, right? They were shacks, basically. And so people would go down, spend the summer, spend the weekends, whatever, to cool off, and then go back to the city. And so I think that, you know, maybe if there was some way for us to think about the coast as a place to go to cool off, right, without this permanent hardening. I mean, Rockaway Park, people live there year-round, right? It's not a it's a vacation community in the sense that there's day trippers, but it's not vacation homes. So that might be one way to think about it. Obviously, all of these, you know, these problems related to climate change are not simple, they are intertwined. We have, you know, people that I'm working with are working on urban forests, and so I think, you know, coupling urban forestry to decrease the heat in the city would also help some of that. But these are wicked problems, right? And they're all intertwined. And this is, again, going back to what I said at the beginning, there's a place for all of us to contribute in this work. There's not going to be any single, you know, there's no miracle here. There's no magic bullet that's going to solve the human problems related to climate change. And so, you know, coordinating that work and seeing those connections, I think, is part of what, you know, students and researchers can get out of an interdisciplinary viewpoint. Nobody's going to toss that, are they?
Somebody pass it back.
Thank you. I'm wondering if you could say a little bit more about how it was when there was managed retreat, how the logistics worked of these homeowners kind of insisting that the land not be redeveloped. Because I'm thinking about places in, say, southern Louisiana, like Cocodrie, where permanent residents leave, and now there are these beautiful fishing camps that kind of take their place. So how did that actually work to say no development here?
So I simplified, and let me now give you a little bit more of the complexity. So in New York, we had two buyouts. We had a city-led buyout, and we had a state-led buyout. The people in Oakwood Beach only wanted to do their buyouts with the state because the state would guarantee that there would not be development on that land. The city did not make that agreement, right? So the city has the potential to develop something there. Now, there are currently, and I'm not totally up to date on this, so you might want to Google this to find even more up-to-date information, but there was a proposal, and I think it did go through for there to be recreational fields built in that area. And the homeowners who had lived there did not want that. They just wanted it to be open space and to be used for recreation. But the difference there was with regard to the agreements that were made by the different buyout, you know, whether it was state or city.
We have those three works of art up front and representing science and policy and politics, or solutions which happen in our country in the political sphere. as a sociologist, could you talk about the spaces between them a little bit and how we fill them in so we don't have three distinct panels up there, we just have one?
Maybe in the Q&A. But let me tell you about an organization at City University of New York. It's called the Science and Resilience Institute at Jamaica Bay. And it's what's called a boundary organization. And what it tries to do is to bring together scientists, communities, stakeholders, policymakers, et cetera, to fill in some of those spaces. And I think it's some of the most important work that students who are thinking about going into this field can do. We need bridge builders. I say in my classes all the time, the scientists know what's going on. We don't know how to address these questions. And so filling in those spaces is really important. One of the things that Science and Resilience Institute at Brooklyn College does, which is related to Chris's work, is a project called FloodNet, where they are working with the city and local communities to place flood sensors throughout New York City that monitor sunny day flooding, not just sunny day flooding, any kind of flooding, so that the city knows where to put resources. And so that's a partnership between the city, Science Resilience Institute, which is really part of City University of New York too, and local communities. So there's people at the Sea Grant also working in that. So there's these kind of institutes whose mission, we have those to do that kind of work. I don't know what the mission is where Chris works, but I think part of what he's doing is also related to that. But we also just really need to have the hard scientists like Katie, like doing her work, so we have, when we need those answers, they're there. And there's some tremendous people who can see the big picture and know how to tap people to put them together. But we absolutely need funding from educational institutions partnered with government and nonprofits to be able to do that work. But it's really important. I do not want to be the person standing between this group and lunch. Thank you.
And I do want to encourage everybody, we will have more time for conversation later in the afternoon. We will have a panel with a little more time to kind of chat with all the speakers today. I want to invite everybody to lunch. We do have lunch available for all. It's up in the Student Center in Crozier-Williams. To get there, I guess well, there's instructions in the program. You right out the front of this building and hang a right, and you're going, it's a straight shot right up past the library, and you'll see the Student Center on the left. And we're going to be upstairs. So you go in the main entrance of the Student Center, just kind of head upstairs and kind of head back, and you'll find lunch waiting. We're going to resume. We're a little behind schedule, but let's try to see if we can maybe get back 1:30-ish for our afternoon talks, and see everybody back then. Thanks. All right, welcome back, everybody. Thanks again for being here. It is like such a beautiful day outside, and we are sitting in the kind of below ground, so it's nice of everybody to be here. I'm really excited about our next two talks and the rest of the afternoon. Just a quick heads up, we're gonna have two sessions back to back. We're gonna have two speakers without a break in between, and then after that we'll take another short coffee break, and then we'll reconvene in here for a panel discussion with all 5 speakers, and that'll be pretty casual, but just a chance to follow up with any questions that might have been accumulating through the day. To introduce our next speaker, I'd like to invite Kaylin Shagru up to the stage. Kaylin is a senior in the Goodwin-Niering Center, botany major and philosophy minor. And yeah, yay. And Kaylin, I actually have the privilege of working with Kaylin on their senior project. It's focusing on Immanuel Kant's aesthetics and garden theory and theory of landscape design. So it's a really cool project. So Kaylin.
Hi everyone, my name is Kaylin Shagru. I'm from Madison, New Jersey, and today I have the pleasure of introducing Elisa Bukolik, who received her PhD from the University of Notre Dame's program in History and Philosophy of Science. Elisa is an accomplished educator. She is a professor at Boston University and an associate professor at Harvard University, where she was a 2021-22 Harvard Radcliffe Fellow. Elisa founded the Phi Geo Group at Boston University, which is a team of faculty and students, graduate and undergraduate, who research and discuss issues in paleontology, ecology, geomorphology, climate and paleoclimate studies, and much more. Elisa's research is primarily about scientific modeling and data in disciplines such as physical sciences and geoscience. She has researched and published on what many scientists are calling the 6th mass extinction, specifically the ways we measure, quantify, and speak about the species going extinct today compared to the genera of organisms that have gone extinct in the past. Her work she'll be sharing with us shortly is regarding sea level measurements, its history, evolution, and the knowledge that can help us today. It is my distinct pleasure to welcome Elisa Bukolik to give her lecture, The Fall and Rise of Sea Level Measurements, A Brief History and Its Philosophical Lessons.
Thank you so much, Kaylin. That was a great introduction. I appreciate that. And a tremendous thank you to Derek for organizing, to Kelly for the amazing coordination, and everyone else who contributed to this event. It's been a real pleasure, and my fellow speakers as well. I've learned a lot from all of you. So I'm going to approach this today as a historian and philosopher of science. And in particular, I'm interested in, as a historian and philosopher of science, how our scientific concepts change over time, and how it is that scientific methodology works and how our concepts evolve as we learn new things about the world. And I'm going to start here with thinking about why it is that scientists first became interested in sea level. And surprisingly, it's not for the reasons that we are interested in it so much today, but rather it was because it was thought that it could provide a universal reference surface, a zero from which all heights could be measured. I'll then turn to an important figure in the history and philosophy of science, William Whewell, who also turned out to be important for thinking about the tides and sea level studies. He was a scientist and a philosopher and a historian. He was a polymath. He contributed to many different fields. I'll talk about how oftentimes in the process of science, we get a proliferation of our concepts in various ways. And this can initially provide a bit of confusion, but then gets resolved in ways that allow us to explore issues much more deeply. We'll talk about how understanding and measuring sea level requires integrating information about both absolute sea level rise and local sea or relative sea level rise, global versus local factors contributing to these things, but also thinking not just about our present anthropogenic contributions to sea level rise, but the importance of considering deep time also. We often forget to think about the deep past, which is still leaving an important fingerprint on the way things are happening today. I'll also talk not just about deep time, but historical time and historical archives and how historians of science can contribute to this process of studying sea level rise. And then I'll try to draw some broader philosophical lessons at the end. Okay, so let me begin by first talking about how it is that scientists first became interested in sea level rise. So here we have the great poet Goethe, and Goethe was fascinated with the work of Alexander von Humboldt. And Humboldt had traveled around the world, loved to measure the heights of various mountains, and he collected this data all around the world. And Goethe wanted to sort of put this all together into these beautiful maps and displays where he would compare the heights of mountains across different continents, across the world. Which mountain was the highest? There was a rush to find the highest point that both of these individuals were quite excited about. And so Goethe was always asking Humboldt for the latest data and how do you measure. And that was a great question of science of the time. How do you compare the heights of mountains on different continents, right? You can't put them next to each other, so you need a common reference. You need a zero to measure from. And the measure was thought to be, the 0 point was thought to be sea level. However, here we have John Lubbock, and he had a book called The Elementary Treatise on the Tides, and he thought this was kind of silly, that all of these people who were doing, whether they were building buildings or measuring mountains, they were referencing the heights of these things to high or low tide. And Lubbock writes, the practice which at present obtains of referring the heights of buildings and mountains to the level of the sea at high or low water mark seems objectionable. The heights of spring or neap tides, although not subject to much uncertainty, are quantities too vague to be used with propriety as standards of reference. Okay? So the concern was, how is it that we take this fluctuating thing, the sea, and make it this common reference that we can use around the Earth? In this project of trying to figure out, Lubbock enlisted the help of his teacher, William Whewell, and as often happens, the teacher's best work comes out of their students' questions, forcing them to explore new concepts. And Whewell then comes on the stage and calls himself a tidologist. He invents new words. As I mentioned before, he's a polymath. He wrote 2 massive volumes on the history of science, history of the inductive sciences. He also wrote 2 massive volumes on the philosophy of the inductive sciences. These are like, not that you know what telephone books probably are still today, but these are these large volumes where he tried to collect all this knowledge. But the science that he was really passionate about was the sea, and trying to understand the nature of sea level and trying to understand the nature of the tides. And that was the science that really motivated him at a time when tidology, if you would call it, or he called it that, was not yet really a science. It was something that was of practical interest to harbor masters and mariners, but it hadn't really come into its own as a subject of science. And Whewell is the one that sort of helped bring that to the center of scientific inquiry in the geosciences. So one of the things that's helpful to sort of think about, or that many people don't know, is that for most of history, science and philosophy were not distinguished. In fact, the same people that we would today call the great philosophers were often engaged in the science of their day and thinking about the scientific methodology of their day. The great scientists were very philosophical in their thinking as well. And indeed, for most of history, the word scientist didn't exist. Rather, the people who were engaged in science were called natural philosophers, or philosophers about nature. And surprisingly, it wasn't until Whewell in 1833 that the term scientist was first introduced into the literature. He did so at an 1833 meeting of the British Association for the Advancement of Science, after which our own AAAS was modeled. And at this meeting, he met the poet Samuel Taylor Coleridge of the Rime of the Ancient Mariner fame. And Coleridge was kind of a cranky old guy, and he's like, you can't use natural philosopher for the kind of work that's being done in science today. The geoscientists were getting their hands dirty. They were digging in the dirt. They were doing experiments in the lab. They weren't these lofty chairs of Cambridge and Oxford sitting in their armchair reflecting on the laws of the world. They were out there getting dirty and messy. And Coleridge thought that the term natural philosopher shouldn't apply to them. So Whewell, being the wordsmith that he was, he coined many words. Uniformitarianism is a word from the geosciences, anoid, cathode, many terms he coined that we use today. But one of the most important words that he coined was the term scientist. So he replied to Coleridge, if philosopher be too wide and lofty a term, then by analogy with the word artist, we may form the word scientist. And interestingly, the first time the word scientist appears in print is in Whewell's review in 1834 of Mary Somerville's book on the connection of the physical sciences. So here was a woman who was writing in the 19th century a textbook on physics at a time when women weren't allowed into universities. They weren't allowed into the institutions of science, into the royal institutions and so forth. She had to be completely self-taught. And she had written this wonderful book on physics, and Whewell was very supportive of women in science and raising up and calling attention to their work and contributions. And he said, we shouldn't be calling her a man of science, right? Instead, the word scientist was introduced. So some people like to say that the very first scientist was a woman. Now, after Whewell took up the process of the tides, he decided that he didn't have enough data to really try to make any progress on the question of the tides. And one of the things that Whewell did that was very innovative was he didn't just think of the tides as a local temporal phenomenon. When is high tide? When is low tide? We think of it very much in terms of time. But what Whewell did was start to think of it in terms of space. So how do the tides move across the earth? How is it what are called, he called cotidal lines, common places of high tide around the earth, common places of low tide? How are these things spatially distributed around the globe? And he was very innovative in developing all sorts of data visualization methods, where he was trying to put together this more global picture of the nature of the sea and the tides, rather than just focusing on what happened at your particular port. So in order to make progress on the science of tidology, Whewell knew that he needed more data. And of course, he wasn't going to be able to collect all the data. It's a big world, right? There's a lot of ocean out there. You can't go and measure the tide at all the different locations around the world. So what he did was he enlisted a huge army of volunteers, 650 from 9 nations around the world. In fact, he put out circulars calling for citizen scientists, or what we today more commonly call community scientists. These are ordinary people from the lay public, and teaching them how to make tide measurements, and then trying to instruct them in how to carry out these measurements so that they had good quality data, and then sending it around the world for people to collect the data and engage in what he called the Great Tide Experiment. And this Great Tide Experiment was 2 intensive weeks where every 15 minutes tidal data was collected from many different points simultaneously around the globe. And of course, this was before computers to process the data. This was before you could, phone up or email the data back to Whewell. He had to wait weeks and weeks for it to travel back on various ships. But when he got this data, he was overwhelmed, not surprisingly. Can you imagine millions of data points with no calculators, no computers, and how do you make sense of this, right? And one of the things that the earth sciences have to struggle with is that they're not doing scientific work in this isolated, clean laboratory for the most part. They're out there in the field, right? They're trying to make measurements out on ships and coasts and storms and all of these very different conditions, which means that the data that's often collected is what we might say noisy, right? We have lots of different causal factors contributing to it. If you're trying to measure rainfall, you might have the wind blowing, right? And so your rainfall measurement might not be exactly right. So this noisy data was one that really led Whewell to think about, how do we deal with noisy data? How do we deal with data that was collected in the field and collected on these large scales by a wide variety of people all over the world? And so one of the things he developed then to manage this was to think about the philosophy of science. So Whewell knew that data do not speak for themselves. You often hear today members of Silicon Valley or big AI or big data people say, the data speak for themselves, the data do not lie. But importantly, data have to be interpreted. They have to be corrected. They have to be processed in order to become evidence. And Whewell recognized that very early on in the 19th century, and he helped develop some of the methods that scientists still use today for data processing. So this work on the Great Tide Experiment, I should just say, is due to the historian of science, Michael Reddy. Has this wonderful book, Tides of History, if you want to read more about Whewell's Great Tide Experiment. So when Whewell is gathering together this vast quantities of data, and he's trying to say, okay, what have I gotten myself into? How do I start to discover what the laws of the sea are? What are the different causal contributions? What are the patterns? What are the principles that should guide from this giant, vast quantity of data? He turned to philosophy of science. And in particular, Whewell's well known for codifying 4 methods of inductive sciences. And these 4 methods of inductive sciences, it's interesting that if you look at his correspondence during this time, he identifies his work on the tides as being the scientific work that really helped him develop this philosophical understanding and new methods, scientific methodology. And it was that scientific methodology that also helped inform the development of his philosophy of science. There was a great synergy between 2 fields that we would consider very distinct today, namely the scientific practice and the philosophy of it. And he thought that they contributed together. So he says, I'm meditating on returning forthwith to my beloved induction. I've been employed hitherto with a thumping paper on the tides, which I intend to take a step of some consequence in the theory. I wish I could explain to you how useful my philosophy is in showing me how to set about on a matter and how good a subject this one of the tides is to exemplify it, right? So again, thinking about how a lot of progress comes from science also thinking about its methodology, reflecting a kind of meta-scientific perspective, if you will. So, as I noted before, Whewell recognizes observations are never perfect. Our senses and our measures are all from various causes, inaccurate to some degree. But what Whewell recognized is that doesn't mean they're useless. That doesn't mean they're wrong. That data can have imperfections, but these imperfections can be measured, they can be corrected, they can be compensated for. Oftentimes that data can still, despite its imperfections, be adequate for various scientific purposes. And so we need to kind of move beyond either the data are perfect mirror of the world or the data are useless. And rather, Whewell carves out this middle space that although data are imperfect, they can give us genuine insight into the world, and we can learn how to make that data better. And this making of data better doesn't always happen at the initial stage of data collection, but sometimes this making data better happens much later, either a week later, a month later, or sometimes a century later. And I'll come back to this idea that we often go back to historical data, and scientists today can take that imperfect historical data and make it useful for science again today. And that was something that Whewell really kind of brought to the forefront of people's recognition. So the methods that Whewell identifies here are ones that had been kind of, percolating around the sciences. The method of least squares was an important statistical method that Gauss had developed in the context of geodesy and the geosciences. It was also used in astronomy. But Whewell really kind of brings them together and gives them a sort of rigorous discussion and attention. The method of curves is where you plot data spatially and draw a curve filling the missing data points and smoothing. So recognizing that when you're engaged in studying the Earth, you can't measure all parts of the Earth, you can't measure all parts of the ocean, right, or the tides. You need to figure out how to interpolate. So he thought about data visualization and drawing methods of curves to fill those missing data points. Method of means, assuming the errors balance each other and can be arranged in classes before you find the mean. This works especially for what we would call random error, but there's this other category of error, systematic error, that Whewell was also aware of. But he understood these methods were useful even if they didn't answer all the problems. Method of least squares I had mentioned before, and he was also particularly famous for the method of residue. And the method of residue is this idea that oftentimes we know some of the causal factors that contribute to an effect. So we might know sea level rise is affected by increasing temperature, thermal expansion of the water, but it might be that sea level is rising more than just that, right? Or maybe rising more than just the meltwater from melting glaciers. And so we look for the residue, that remainder of the phenomena that can't be accounted for by the causes we already know, and we use that to discover new causes, new contributions to sea level rise that we didn't recognize before. And we'll see an example of that. Actually, we heard about it already from Chris this morning, gravity, but I'll come back to that. So despite the power of these methods, Whewell notes that they are no substitute for adequate conceptualizations of the phenomena. So this is interesting, right? Normally we sort of think of data as these things that are just independent out there in the world. The numbers are just these objective things. But these numbers depend on concepts. They depend on what we think we're measuring, how we measured it, the instruments that we use to measure it. And so it's important that we think about not just the numbers themselves, but the concepts upon which these numbers rest. And this kind of conceptual analysis is the sort of thing that philosophers of science love to do. We love to think about the concepts that we use to organize and classify the world and press those concepts and see, do we maybe need to take this concept that we've had for a long time and realize that it describes two different concepts instead of just one? So thinking about those bifurcations of our concepts over time. So Whewell famously said, facts are the materials of science, but all facts involve ideas. And you can't just give up the data, the numbers to go off by themselves. You've got to do the hard work as a scientist to think about the concepts that are used to categorize and organize and identify those data. An important lesson, I think, for data science today, where you often get the impression that data science can happen without the conceptual work. Whewell would say no. Okay, so here, this is too small to see, but here's one of Whewell's maps of the cotidal lines. And these cotidal lines was the sort of concept that he thought needed to be sort of imposed upon the data to organize it in various ways. And so he introduced the term a colligation of facts, which is the mental operation of bringing together a number of different empirical facts or a collection of data and superinducing upon them a conception which unites the facts and renders them capable of being expressed by a general law. Whewell's favorite example of a colligation of the facts was Kepler, who in discovering had all this data, astronomical data about planetary motion, and had the concept of an ellipse to describe the motion of the planets. And that was, for Whewell, a great model of the importance of having the right concepts. And the data won't be exactly perfect, but once you get that correct concept, then you can move forward and make further progress in that science. So another concept besides the tides that Whewell refined was sea level, our topic for today. So drawing on his methods of curves and the extensive data that he had gotten in the Great Tide Experiment, he showed graphically by means of continuous curves how the heights of tides varied at locations such as Plymouth in England and Singapore. And making use of his method of means, he then drew lines representing the mean height, the midpoint between the high and low water, and taking the mean of the two curves, which he does for these two locations, and showing that the mean sea level, even though high and low tide varied, the mean sea level seemed in these cases very nearly constant. Okay? So by using his method of inductive sciences, he turned the community from focusing on high water, low water, to the idea of mean sea level. Okay? And mean sea level seemed to be something that could be a little bit more universally applied around the world, although he famously says very nearly so. So this was important in thinking of global mean sea level as what's called a fixed vertical datum. That's just the technical term for the zero mark that heights are measured from. And I'm going to tell you a little bit about the history of thinking about sea level as a vertical datum, as a 0 point for much of recent history. So beginning in 1864, the International Association of Geodesy encouraged countries around the world to undertake local measurements of mean sea level and then try to connect them through various surveying levels. So the idea was to engage in this global science. Geodesy and the earth sciences are one of the sciences where you can't just sort of be alone in your own country, in your own lab by yourself. You need to coordinate with researchers around the world. It needs to be a global endeavor. If we don't have measurements in some part of the Earth, we don't understand the Earth. So it really was one of the sciences that emphasized the importance of international collaboration and international communication and sharing of data and knowledge across national boundaries. And that was very important in the development of science today. And unfortunately, some things that are under threat in various ways. But I think it's a value that we still want to hold on to, that we learned from the earth sciences, the importance of international collaboration to make progress in science. Oh, a little bit closer to that. Thank you. I tend to walk around a lot. Good. So, what was interesting is that when the various countries undertook this project of trying to determine the mean sea level, right? So now they had focused on this mean sea level idea and measured it along the various coasts of a particular country. They found that the numbers didn't agree, and this was a great puzzle. So for example, here, this is in England. They completed the leveling from Newland to Dunbar, and they had a difference of mean sea level that was far greater than the probable error. So they knew they weren't going to get exactly the mean sea level because, as Huell said, the data are never perfect. But if you understand the sources of error and uncertainty, you should say we should at least fall within that uncertainty cone, right? And yet they weren't. They weren't falling within that. They were falling outside of it. That suggests that there's something new that they hadn't yet discovered, some new factor that they had overlooked, right? When your numbers should agree and they don't, that discordance is actually one of the great drivers of science, right? It's when data disagree that we learn new things. We love it when data agree, then our life is easy, we get to go home early, be with our family, close lab. But when data disagree, that's that frustrating moment, that's where we make new discoveries and new insights. And so they discovered that there was this difference. And as a result of that, at that time, they didn't have the resources to fully understand all the factors that were contributing to the differences in sea level along the UK coast. But they still had to figure out, what are we going to measure these things against, right? In a way, you need to have some sort of framework for making measurements, something to measure sea level rise rates and heights from in order to have a conversation about these things. And so that framework is sort of that hidden structure part of science that often gets overlooked, but was very important and drove much of sea level research. So they picked just this one location. Here you can go see a little plaque. The ordnance datum of Newland is the national vertical datum, to which all heights in the UK are still referenced as their zero. And you can see the little plaque there. This attempt to try to fix a 0 point somewhere on the Earth, right? As we know, though, these physical markers, although they're so conceptually important for establishing all of these measurements and making them coherent and commensurable and comparable in some way, we know that the Earth is also in flux. So I'll come back to that issue as well. I think of it as trying to measure a Heraclitan world without an Archimedean place to stand. Remember, Archimedes says, give me a lever and a place to stand and I can move the Earth. But there is no such place outside the Earth to move the Earth, right? That's the problem of the Archimedean point. And a Heraclitan world, the pre-Socratic philosopher, all is flux. You can never step in the same river twice. And so what we're learning in the earth sciences is that we live in a very dynamic processual world. And yet to do good high-precision science, we need to get some sort of Archimedean place to stand from which to measure, to make these high-precision measurements. So how do we establish this kind of framework? Sea level studies were very important in that process. So while the UK was smart and only went to one site, the US tried to do it for 26 gauge sites along all the coast. So here's the national sea level datum of 1929, had all of these different points around the coast that was used to define the zero, against which all heights in the US were measured on all maps. All elevations that you would see on a map were measured to these zeros. And the problem was they weren't all actually at the same height. They stipulated them to be zero, but in fact, they varied quite markedly. And so here we have a problem. No two determinations of mean sea level at different localities will be on the same level surface and will therefore have different elevations as determined by different leveling processes. And this was a problem, right? You need to kind of develop a framework for measuring heights that's consistent, at least across the US, you would hope, even if not internationally. And that was a challenge. So mean sea levels vary from place to place. There are a number of different factors that contribute to it. Topography, issues of the geoid, which I'll come back to in a moment, differences in temperature, salinity, ocean currents. And these mean sea levels at different locations can vary on the order of meters. So this wasn't a difference that could be neglected. It was something that the scientific community had to confront. And this idea that we could just stipulate them to be the same, sea level, mean sea level, as the common number 0 did not work. So the sea level datum became more abstracted away from sea level. So scientists started to realize we really shouldn't be thinking of this as sea level anymore. We need to get an abstract reference system. The science of geodesy is interested in this procedure. Finally, the National Vertical Datum of 1988 picked a single location here in Quebec, just like was done in the UK, and that was eventually stipulated to be the 0 point from which all heights in North America were measured. Interestingly, this process of trying to get this Archimedean point, of trying to get this framework from making these measures, is something that science is iteratively improving. So we are about to enter in the North American Geopolitical Datum of 2022. They're always about 5 years behind the date that's given, so they're not actually implemented in the year that's listed there. I think they just recently released the beta version, but it hasn't been fully launched yet. And the idea here is to try to move away from using these markers from tide gauge data at a particular location to using satellite data in the International Terrestrial Reference System. But I won't talk about that more. I'm happy to come back to it. Okay, so what is this concept of the geoid, right? This is probably a word you haven't encountered before. But although we tend to think of the Earth as this perfect sphere, of course it's a little bit squished, you know, like a beach ball that's squished, more ellipsoid bulging at the equator, but it's actually also a little bit more like this lumpy thing over here. Now the vertical scale has been exaggerated so you can see it, but this shape is actually a more accurate representation of the shape of the Earth. And what this shape represents is what we call a gravitational equipotential surface. A lot of scary words, but don't worry. All it means is that if you put a marble on any location on that lumpy surface, it won't roll. It'll stay put, okay? No water will flow, no marbles will roll. That's what level is, okay? So the geoid defines the level surface of the Earth. And why is it so lumpy? Well, it's because there's different masses underneath at various locations. And that you have to then get different heights to balance that gravitational force and make it the same across the globe. So this concept of the geoid, again, we kind of are moving for thinking about what is the shape of the Earth, and that has evolved over time and bifurcated into these different concepts, the geoid being one of them. All right, so this is the shape that the Earth would take if it were just under the force of gravity and Earth's rotation alone. So if it was a purely ocean world, there were no continents, that's what the shape of the Earth would be like under the force of gravity alone. However, as progress happened, this approach to thinking about this as mean sea level, the geoid as defining mean sea level, became more and more problematic. And so the idea was that we had to start to distinguish these different concepts in various ways. The geoid is something that still needs to be measured carefully with gravitational measurements. And some of the satellites that Chris talked about this morning also need to take into account gravity data, even in the case of satellite data. So identifying mean sea level as the 0 vertical height, although we can understand why that was the initial thrust of the scientific research on sea level around the world, it began to be problematic because it erased one of the phenomenons that was most needed to be studied, namely how sea level was changing, how sea level varied. And so the idea of a 0 had to be abstracted away from this physical idea of sea level so that sea level itself could be measured and its changes tracked over time in a way that could be compared consistently. So I put it here, sea level had to transform from a fixed reference yardstick to a dynamic measurand. Measurand just means the quantity you're trying to measure. So it went from being the thing that does the measuring to the thing being measured. Another further challenge in this history is that measuring sea level isn't going to just depend on the sea, it's going to depend on the earth. And so the solid earth is also something that is dynamic. As we heard very nicely from Chris's presentation, we have uplift, we have subsidence, we have tectonics, we have differences happening in the earth, in its elevations in different places. So the solid earth is also, there's also actually a very interesting phenomenon called solid body tides. Not only the earth undergoes the tides, but the solid earth also rises and falls, usually twice a day. But we don't detect it, right? It's imperceptible to us. But just as the forces pull on the oceans, they also pull on the solid earth. So there's complex tidal phenomena on the solid body earth as well as on the sea. And when you're trying to measure sea level rise and change, right, you have to be thinking about all of these different forces, what's changing in the solid earth and what's changing in the sea. And often what you're measuring is a complex combination of those things. So the land can be rising, uplifting, or falling, subsiding due to factors such as glacial isostatic adjustment, rising where the massive ice sheets from the last glacial maximum 21,000 years ago are receding. But there's also, as we heard today, issues of at the very margin of those ice sheets, there is what's called the forebulge. So if you imagine that I had a water balloon in my hand and I press down on one side of the water balloon, it's going to bulge up on the other side, right? That's like the ice sheet pressing down. And then I remove my hand from that water balloon, that bulge is going to fall back down, right? That's what's happening in places like Maryland, where relative sea level rise is greatly accelerated, right? It's not just that we have the global sea level rise contributing to the rising water, but we have the earth falling in this location that is compounding those effects and contributing to relative sea level rise. There's also a number, so this is some of the causal factors coming from deep time. So when I say that we need to be thinking about history, not just human history, but deep time history, to understand what's happening to the earth today, we need to know what happened to the earth 10,000, a million, and so on years ago, because those fingerprints of those causal factors are still with us today. Our earth today is like a palimpsest with many different writings upon it from the different ages of the earth. And we have to learn to read not just the most recent book that was there, but the ones that were erased underneath it and still are contributing in various ways. So tide gauges, recall, measure relative sea level, which is a net vertical movement between the land and the sea. And so as we said, rapid uplift, relative sea level drop can happen despite global sea level rise. And so we kind of, again, had another bifurcation of our concepts, right? We went from high water, low water, to mean sea level, and then we think about relative sea level versus absolute sea level rise. We're seeing that as science progresses, we're having to sort of carve off these different concepts and start to keep them clear in our mind in various ways. We need to think not just about the moving of the oceans, but the moving of the earth. Okay. So when we think about understanding sea level rise, as we talked about before, and many other speakers have pointed out, the two common things that people think about are the global warming that's contributing to the thermal expansion of the water. A warmer ocean takes up more volume than a colder one. But also, as the glaciers and ice sheets are melting, water is being transported from the land into the sea, right? And so about, I think, 200 billion tons of ice each year in the form of meltwater are being added to the sea. And the Antarctic ice sheet alone has the capacity to raise the world ocean over 60 meters or 200 feet. So there's a lot of water to be transferred there. But importantly, these are not the only two factors. And it's interesting that it was only in about the 2010s that a third causal factor was discovered. And this was talked about by Chris earlier. But what I find interesting is that for a long time, so there was a wonderful interview by the geophysical dynamicist Stauffer, who said this third factor was like a gorilla in the room that nobody saw. People were thinking about sea level rise in terms of those first two factors, but they had forgotten about the importance of gravity in contributing to sea level rise. And so a third factor is thinking about how the geoid itself gets changed as the gravitational mass on the Earth moves around. So as we heard this morning, that massive Antarctic ice sheet. So here's the Antarctic ice sheet. Look how big it is, right, compared to the continental US. It's huge, right? And it's 2 kilometers thick in some 30 million cubic kilometers of ice. So this is a massive amount of ice. And that massive amount of ice has a strong gravitational pull. And it's not just holding the water itself, the ice, but it's actually pulling up the oceans of the Earth up around it. And so it's actually holding the sea closer, the liquid sea, not just what's contained in the ice, but the sea around it closer. So as that ice melts, not only do we get the meltwater going into the ocean, but it's also loosening its grips on the world's ocean. Now, as we heard before, that means that sea level is actually going to fall in the region of the melting ice sheets and not rise. We often think, those melting glaciers, that's somewhere else in the world. We don't need to worry about that. We don't have any melting glaciers here. But it's actually the opposite. What's happening to those melting glaciers is not going to impact those local communities the hardest first. It's going to impact us who are far away. So again, we need to start to think more globally as well as locally about sea level rise. Things that are happening far away might affect us more. It might be that sea level near these Antarctic ice sheets, for example, or the Greenland ice sheets we heard about this morning, sea level is falling there, but it's rising elsewhere, and it's rising here, for example. So this suggests that what we might think of as sort of the bathtub model, right? Oh, the ice melts, we get more water, but it just evenly distributes to the bathtub, the Earth. No, there's actually very interesting differences due to the gravitational geoid surface and how that water is going to be distributed around the globe. And that's a dynamic thing that needs to be modeled and studied by scientists to understand how that water is going to be redistributed and where. And so Jerry Mitrovica at Harvard University is one of the scientists who's been working on this problem that I've enjoyed learning from. Okay, so to take a step back, we have learned that understanding and measuring sea level requires bringing together these sort of different, seemingly contrary elements, right? We need to keep in mind global sea level rise, but also relative sea level rise, right? We need to keep in, absolute versus relative. We need to keep in mind global causal factors contributing to sea level rise and local causal factors, our own geologic history of where we live, our particular spot. Is our land rising or falling? Was it under the glacier, at the forebulge of the glacier, and so forth? We need to keep in mind the present, our anthropogenic contributions to global warming and to sea level rise, and at the same time, deep time. These things all need to come together. And so this requires lots more data and new models to know how to combine these factors to actually make predictions that are going to be useful for planners, trying to decide how high do we need to make the building codes, right, for how high you need to build your house if it's going to be in a floodplain, for example. Okay, so now getting more data to build better models to understand how all these causal factors come together is challenging because our instrument data record for sea level only goes back about a century, right? We don't have a very long record. And yet, the things we want to do is predict far into the future. The more data we have going back in time, the better models we can build to help project into our future where we're headed. The more we can reduce uncertainty about various factors. But for the most part, that data instrument record is relatively short. However, there are some records that are hidden in various dusty archives of individual scientists or natural philosophers in various libraries around the world. And so here is a way in which historians of science can actually help contribute to the study of sea level rise by identifying records of sea level rise at various locations that go back much further in time than the official NOAA tide gauge data. So the NOAA tide gauge data only goes back in Boston to 1921, but it turns out that there was a civil engineer by the name of Lawami Baldwin Jr. Baldwin was somebody who was engaged in building in Charleston, where ships were built. So if you know of old Ironsides, the USS Constitution, where it was fixed, that was there in his dry dock. So he, in building this dry dock in Charlestown, actually took very careful, meticulous sea level measurements of the Boston Harbor over a long period of time. And this data is what we call dark data, because this data was forgotten from science. It was stored in his personal notes, handwritten in a dusty archive in Harvard's library. Right? And yet, having historians of science working with climate science and geoscientists, they can help identify, the historians of science can help identify this data and then make it available to scientists who then can recurate, reprocess, and validate this historical data. And this project was undertaken by these scientists here, Taki et al. In 2018, where they went through the process of taking Baldwin's sea level data, and they had to figure out what was the 0 point that he was measuring from, right? If you want to take his sea level measurements and compare it to the modern NOAA sea level measurements, you need to make sure they're being measured from the same 0, right? So that was important to make it what Kuhn might say, call it commensurable data, right? The data needed to be comparable in order to be combined. But scientists also needed to clean up the data. They needed to understand what errors maybe happened in the instruments that Baldwin used. Had the benchmark that he had used as his vertical datum, had it subsided or uplifted, had it moved? And so they did all sorts of cross-validation with 4 different methods, measuring with other datums across Boston. One was at the Boston Museum of Fine Arts, for example. These little plaques that you might know, the geodetic markers that you find sometimes when you're walking in various cities and so forth. They cross-checked all this data, and they were able to make it commensurable with the NOAA data. And in doing so, they were able to double the length of the sea level data in Boston. And because of the work, this historical work, identifying and recurating and reprocessing, bringing this dark data to light, then it was the case that now Boston has one of the longest known water level records outside of Northern Europe. Okay? So again, I think it kind of shows us how important it is that historians and philosophers come and work with scientists, right? We all need to be working together, citizen scientists as well, collecting data, finding ways to get more information to help understand how our Earth is dynamically changing. Okay. So let me draw some philosophical lessons now. So first of all, as Whewell recognized, when it comes to understanding the sea, it's all hands on deck. And I think, Whewell was one who really recognized the importance of a diverse representation in science, including the public. The public needs to become community scientists, what we used to call citizen science. People like the word community better these days because you don't have to be citizens of a country. You can be from anywhere and still contribute to science. And so we need to bring all people on board for gathering the data that we need to understand and make progress on these important wicked problems, as we heard earlier today. As Whewell also recognized, these data don't speak for themselves. Scientists must learn how to extract the signal of sea level rise from noisy, messy data that might have been collected under imperfect conditions, but can still be useful if we can find out what those imperfect conditions were. And again, historians of science can tell us, well, these were the instruments they were using. Maybe they even have the instruments still in these wonderful museums. At Harvard, there's a wonderful museum for scientific instruments. And sometimes scientists will actually go back and measure the error associated with a particular historic instrument, and now they can take the data that was produced by that instrument and use it again, because they understand what its sources of error are. So again, we see this wonderful collaborative opportunity between the humanities and the sciences. One of the things that I've been interested in is this issue, this process of data correction. So my own work towards a taxonomy of the models of data, how it is models are used to correct data, understanding data uncertainty, using models to correct data, and then thinking about how data even though it's not perfect, can still be adequate purpose, right? Rather than saying good data, bad data, is the data usable for the questions you want to ask? It may not answer all questions you want to ask, but oftentimes it's adequate for answering some questions. So learning to distinguish that and not throw it out. Third, just as important as developing data and theories is developing adequate conceptualizations of the phenomena and refining scientific concepts over time. We often forget about that important conceptual work that scientists do. How do we conceptualize the world? How do we categorize the world, right? Do we want high water, low water, mean sea level, relative sea level? Do we want the ellipsoid shape of the Earth, the geoid shape of the Earth? As science progresses, we find that what we thought were these simple concepts actually capture a rich complexity of our world, and that oftentimes we then have to carve off different versions as our understanding progresses in order to get higher and higher precision measurements and more accuracy in our methods. So again, the data numbers are meaningless apart from the complex historical network of ideas that they rest on, right? So we need to keep that conceptual work in mind when we're working with data. And this is why when we think about putting data together in these giant databases, metadata is so important. I don't know if you've heard of metadata. Metadata are data about the data. So where did these data come from? Who measured them? When? Under what conditions? Using what instruments? That metadata is what makes that data continue to be useful beyond its original purpose for collection. That's why it can be useful. Like Loami Bolden's data, why it could be useful a century later was because the historians of science helped collect that metadata that was needed to make it comparable with our data today. Fourth, we need to preserve these historical archives. We need to preserve these databases. We need to invest in the infrastructure for the long-term preservation of this data and for the rescue of this data. There are lots of community science projects, for example, looking at old ship's logs and reports of weather that are then being digitized. That's the kind of data curation, collection process that takes this dark, lost data that is useless because nobody knows about it anymore and brings it up to be useful for science again. And so again, thinking about this process is we need to preserve those data. And sometimes the data could be on a substrate. For example, I think I still own a floppy drive. That tells you how old I am. You know the icon for saving? Most of you kids have no idea what that is. That's how you used to save things. But we don't have things to read that anymore. So any data that's on those things could be lost unless we recurate. So thinking about data and how do we continue to make data useful? How do we continue to make data accessible to future scientists who might discover new ways of extracting new discoveries from things that were collected in the past, right? The history is important for our future, right? We need to collect these things. And then finally, or penultimately, I like, as a philosopher, to sort of think about this idea of processualism. What is processualism? Well, processualism is the idea that we shouldn't just be thinking of the world as being composed of objects, but rather we should also be thinking of the world as composed of processes, thinking of things as changing over time. I have here a book, Timefulness by Marcia Bjornerud. I highly recommend this book. She makes an interesting claim. She says we should think about rocks not as nouns, but as verbs. What does that mean to think of a rock as a verb? To think of something as it's dynamic, as it's moving, as it's changing, right? Just because it's on a time scale that we don't notice on a day-to-day basis doesn't mean that change doesn't matter. So how is it that we can kind of change the way we perceive the world if we think of it as being a tangle of processes rather than just a set of objects that are fixed? Even the mountains are changing. One of the most striking examples of this are the fossils of the marine organisms at the top of Mount Everest. The top of Mount Everest has fossils of things that lived at the bottom of the sea. That's how much mountains change. We need to start to think about our Earth as a dynamic, changing entity, not as something fixed, not as something where we are insignificant, but as something where we have now become a geologic force. We are transforming the world, and the world is a dynamic, tangle of these various processes that are unfolding at many different spatial scales and many different temporal scales. And so Marcia Bjornerode in her book Timefulness says we need to start thinking multi-temporally. We need to start bringing the past, both human history with these historical archives from the history of science, but also Earth's deep past with us today. And it's this thinking like a geologist with a deep time that's going to help us navigate the threats that are happening today with our future. And so I'll leave you with that recommendation for timefulness and thinking about how history, philosophy, the public, all of us can come together to make progress on these important problems. Thank you. That's right. Got to whack the ball to get it to work. You can just be loud. I'm loud. Yes.
Field of experts, of historians of science.
Yes.
It's 67 years old.
Right.
So are there any other books, histories of science, authors that you would recommend? Hey, this has made waves since then, and I'd recommend, it maybe hasn't made it beyond the experts. Something that's, a response to Kuhn that was published afterwards.
So you're asking for recommendations of post-Kuhn philosophy of science? Is that what your question is? Yeah, so there's a ton of great work. I mean, so what I would do it as I would ask, what is the question that you're interested in? So Kuhn was primarily interested in theory change, and so that was one topic, but there's lots of exciting work in the philosophy of measurement, the philosophy of data, and so maybe we could follow up afterwards, and I could find out what questions you're interested in. I'd give you a very long reading list. I've lots to recommend. Thank you. But I'd also say look back, right? I mean, Kuhn is well known, but Whewell has been forgotten, and I think Whewell is just as valuable as Kuhn. Yeah. Yes.
Half of the 1800s. As I'm sure you know, another region that was motivated to do a lot of innovative sea level work was along the Baltic and the Swedish coast, because this is one of the most habited places that was experiencing really dramatic uplift from glacial isostatic adjustment. Were the Swedish sea level geodesy community folks in contact with Whewell? Because he seemed to be sort of, I think, perplexed by some of the questions that had come up since the 1700s along the Swedish coast.
Yeah, no, that's very interesting. I don't know the Swedish scientists that were involved. There was a lot in the Prussian scientists, so geodesy, the International Association of Geodesy, was attempting to become this, it actually I think was the first international scientific organization that was really trying to pull together multiple countries. I don't know which country, whether this was included in that community, but this was at a time when there just weren't people necessarily working in the geosciences, although there were lay people who were obviously tracking this, noticing it, trying to understand why it was happening and its importance. But we really kind of see in the 19th century this kind of formalization of these studies as an area of science. So we see the first scientific organizations of geodesy emerging. We see the first scientific journals. And I think you're right that it did become this global phenomenon in this important way. And it's interesting that it is the geodesists who were kind of leading that way towards high precision measurement, that international community of geodesists that was leading towards high precision measurement in a way that wasn't happening in the other sciences. And so I'm sure you're familiar with the science of metrology. Metrology is the most important science you've never heard of. So metrology is not meteorology, not the weather. Metrology is the science of measurement. So how do we all make sure we're measuring the same thing? So you may have heard about metrology recently through the redefinition of the kilogram. Do you remember when that happened? But it was the geodesists who established the meter bar as being the standard and the International Bureau for Weights and Measures. And so there really was this international community. I don't know which all countries were represented within this organization, but that were working together to try to establish an international science that we're all speaking the same language, if you were. They're all using the same unit. I mean, the US still hasn't gotten on board with the meter and the kilogram, but we're working on it. But really, like, that's how that's important for, if we're gonna do global science, we need to make sure our numbers and our concepts speak to each other, right, in a meaningful way. And so I think you're right that all of these countries were contributing in some way, but I don't know the particular history there. I look forward to hearing more about it. Thanks. There's one there.
Thank you for that. I thought it was really interesting when you said sea level went from being a measurement tool from which we measured things from to being the thing being measured.
Yeah.
And so I kind of have a two-part question. The first is, like, at what point in the timeline did that really happen noticeably, I guess? And then when we think about sea level as a mean sea level, MSL, right, as a measuring tool, we think of Mount Everest as 49,000 feet above sea level, right, mean sea level. Badwater Basin, I think there's a sign that says like 290 feet below sea level.
Yeah.
Do you think communicating using mean sea level as a reference now does discredit to our broad understanding of the time and spatial variability of sea level?
That is a brilliant question. Thank you so much for asking it, because that actually is a point that I wanted to try to communicate, which is that oftentimes our sort of public understanding of these changes that have happened in science can be far beyond, behind the times, right? And so, we still talk about the sun rising and setting, even though the Copernican revolution happened in the 15th century. But this idea of sea level, we can't be thinking of it as this fixed reference that's permanent, right? And I think using that language does sort of create these challenges in that people don't understand it or think of it as strongly as a dynamic object. And that maybe by changing our language, even though it's not a great language, vertical datum, but it is a way that helps carve off sea level as something that is not supposed to be fixed, that something that is dynamic and is to be measured. And so I think you're right that in some sense that leftover, right, of still using the word measurement from sea level is an artifact of that history, but one that could be inhibiting broader public understanding of the dynamic nature of the oceans. Yeah. Thank you. Thank you all for great questions. Thank you.
Awesome, thank you. I'm gonna advance this. All right. Quick request before I introduce our next introducer. Our next speaker of the day, the session is going to include a screening of a short film, and I just wanted to kindly request that nobody record the film or pass it along. It's not kind of for broader public consumption yet, so we're going to cut the live feed when we show the film. It's really just for us today. So thanks for honoring that. Our next student introducer, I've lost track of my notes. Oh my gosh, is Gabby Leal, who is, so Gabby and I were talking this morning. Gabby is like a triple major. And I wrote this down, and Gabby, I hope I get this right. It's dance and anthropology and architectural studies. Did I get this right? I hope so. Yes. And Gabby is working on an honors thesis this year on biophilic design that I'm really excited. I get to be a second reader on that thesis this year, so I'm excited about that. So Gabby, come on up.
Hi everyone, my name is Gabby and I'm from California. Today I have the pleasure of introducing Dr. Kelsey Leonard, a leading expert in water governance and Indigenous water rights. Dr. Leonard is an associate professor and Canada Research Chair in Indigenous Waters, Climate and Sustainability at the University of Waterloo. She is also an enrolled citizen of the Shinnecock Nation, originally from Shinnecock Indian Reservation on Long Island, New York. Her academic journey is truly remarkable. She was the first member of her community to graduate from Harvard University and the first Native American woman to earn a science degree from the University of Oxford. Her work focuses on Indigenous water justice and explores how climate, governance, and cultural knowledge intersect to shape sustainable water futures. Dr. Leonard has collaborated with global scholars and policymakers, contributed to international legal discussions on Indigenous rights, and published influential research on water governance. She has also served on major environmental boards, helping protect vital ecosystems and advocate for Indigenous perspectives and policy. One of her well-known ideas is the concept of granting legal rights to rivers and lakes, which she explores in her widely viewed TED Talk. Why lakes and rivers should have the same rights as humans. I suggest that you guys all give it a look after this. It is truly an honor to have her with us today. Please join me in welcoming Dr. Kelsey Leonard as she presents her talk, Rising Seas, Rising Voices, Indigenous Adaptation, the Wampum Framework, and the Women of Wampum. Thank you.
All right. Akwe Winikasat Kalo. Good day, everyone. Thank you so much to Derek, to Kelly, to all of the staff and faculty, and to Gabby for that wonderful introduction, for inviting me to be here with you all today. And thank you all for being here, especially with this lovely weather that we're having. I know being indoors today, talking about rising seas is probably a stark juxtaposition, but we are happy to have you. So my name is Dr. Kelsey Leonard. As Gabby mentioned, I am Shinnecock, and I come to this conversation as both a scholar and as an Indigenous woman whose community continues to live with the realities of coastal change. So when I'm talking with you today about sea level rise, adaptation, and water security, I'm not speaking about an abstract future. I'm speaking about the homelands that are currently under threat in my home territory. I am speaking about relatives. I am speaking about governance, responsibility, and survival as humans and other kin on this planet. So this talk is called Rising Seas, Rising Voices, because too often the story of sea level rise, full credit and thanks to my earlier panelists for giving me this bit of background information that filled all of your ears today. But we heard a lot about numbers, about models, about projections, and about maps. And they are valid and valuable to this conversation. However, they are not the entirety of our story. Because embedded within that story are the voices of each and every one of you, alongside myself and my community and Indigenous peoples. Our voices are not secondary, optional, or symbolic. They're integral to how we have a shared sustainable future. As Indigenous peoples, we are among the oldest stewards of this world and of this territory. We carry vast knowledge systems and legal orders and responsibilities that long predate this current climate crisis we exist within, and that long predate the current institutions and policies and laws trying to manage these wicked problems, as were mentioned earlier. And here in Connecticut and across New England, there is a fundamental misunderstanding that is especially sharp. Many people live on or near Indigenous homelands and waters. They benefit from Indigenous place names. They celebrate a shallow version of this regional history. and yet they still do not understand the tribal nations living beside them. They still do not understand us as sovereign nations. They do not understand that indigenous science is science. And they fundamentally do not understand that indigenous knowledge is not folklore or anecdote. It is method. It is observation over millennia. It is governance and it is law. And in many cases, it is precisely the knowledge needed to respond to these pressing environmental changes we are all grappling with. So today, I want to invite you to listen differently. And it's important in that context to begin with place. Place matters. This map situates Shinnecock Territory in what is now called Suffolk County, New York. And I want to be very clear when I say Shinnecock. I am not referring to vanished indigenous peoples, as is often thought of us. We hold most of what you see here is our traditional territory of the east end of Long Island. You saw the western portion, which some of you know as New York City. But these are our traditional territories and homelands. We are a people that were never removed, and we are still on our ancestral homeland. And so we are bordered by the towns of Hampton Bays and Southampton, and that creates a stark contrast for environmental governance in today's 21st century world. But we're also a people that have been inherently shaped by the water and have shaped the water. We are bay people, we are whalers. We are known for harvesting of wampum, of quahogs, of different mollusk relatives like whelks. And into that became wampum, the beads, and so much more than that, as you'll hear today. But those beads that were carved, they form the treaty belts that govern as the transboundary agreements, the first transboundary and international agreements of what we currently know today as Canada and the United States. So for many audience members today, this region and the maps, they are important because they often try to communicate a common habit of seeing indigenous peoples not on the map. And so it's important that we right those wrongs, that we right that erasure, that as indigenous peoples, we're not somewhere far away or somewhere removed from the east. Despite everything that was placed against us, we are still here. We are still prominent in New England. So let's talk then a bit about sea level rise. How did we get to this unique space and place of time? So when we think about sea level rise and indigenous peoples, we're thinking about concepts that go beyond, as I mentioned earlier, the models, the numbers. We're thinking about the ways in which ocean justice is implicated, sovereignty, cultural continuity, governance. You may have heard a term called land back or water back. These are the ways in which we reimagine the settler colonial system to allow for there to be ecological healing for both humans and non-humans on this planet. So when many people hear sea level rise, they think of flooded roads, expensive homes, or insurance claims, all valid, and we heard of that earlier today. But for indigenous peoples, sea level rise must be understood much more broadly. It is about ocean justice, it is about sovereignty, it's about our cultural continuity. It's about each and every one of you in this room, future generations of humans and non-humans being able to live together and thrive and flourish. And when we think about our animal kin, they are particularly impacted. From mollusks to fish to birds, eelgrass, wetlands, the living systems that sustain us and with whom we are in relationship with, they are also under pressure and they deserve to be protected. Their habitats are shifting, their patterns are changing, and they matter. They matter not only because they support human life, but because they are relatives in their own right. So sea level rise also does not arrive on neutral ground. It arrives in places already shaped by dispossession, underinvestment, jurisdictional complexity and constraint, and environmental racism. So for tribal nations, this is not only a physical process, it is also political and legal. The question is not simply whether water is rising or moving inland. The question is whether we can continue to live in right relation with homeland and with other more than human kin under conditions that are and were not of our own making. So you're going to hear a lot today about something called wampum. I've mentioned it already. You may have heard about it in a far distant or current history class. You probably heard it all wrong, because I haven't actually heard anyone, aside from Indigenous peoples, and particularly Indigenous women, as you'll hear from later, actually describe what wampum is, was, and will be. It first and foremost is a relative. It's a form of justice. It's living law that is practiced by Indigenous peoples from across Turtle Island. It is embedded ecological knowledge, and it is memory. And some of you may be familiar with the quahogs that you see on the screen, Northern Mercenaria. They are an amazing species. We've heard from so many wonderful academics, and maybe some of you in the room as well are familiar with this. When we look at shell middens and the archaeological record of our home territory, some of these species have been dated to be over 500 years old. They live very long lives. They also are known as filter feeders. They are able, you can pull up on YouTube if you'd like, a video of quahogs filtering in a tank, very sort of perhaps brackish, some might say dirty, but just unbalanced water. You leave them in that tank for an hour or so, and the water turns to what some might argue is a more pristine, clean water. That's what they do for many of our estuary and bay systems. It's something that as Indigenous peoples we've understood about this species for thousands of years, and it's also why they became the ecological record of law and diplomacy and truth. Because the way that we understand how they exist in our world is they are truth seekers. They filter out the bad in our world and give out good. And in using them to create and tell story and to create treaty and agreements and law, it was known that in utilizing that particular species, you were embodying a commitment to truth, that you wouldn't put bad things out into the world. And to understand that that is a part of the epistemology of many Indigenous nations from this region is a fundamental transformation of how we think and should think about coastal restoration and about what it means to call these places home. So when we think about wampum, it really emerges again from our mollusk relatives and from these coastal ecologies. They are inseparable marine life, and they are inseparable from the shoreline. So when I speak of the wampum adaptation framework later in the talk, I'm not borrowing a cultural word for a policy tool. I'm trying to ground our understanding of climate governance, of adaptation, in Indigenous legal and relational system that is still alive today. So let's take a look at what brought me to this work beyond being a Shinnecock woman and scientist. This is a picture of a portion of our home territory on Long Island. You can see here that we live on a peninsula surrounded by water, as well with a barrier island and then the Atlantic Ocean. This is from NOAA's sea level rise simulator from a few years back, so some of the current projections and modeling that we heard today. So this is the territory that we live on. And so climate change is raising seas, it's shifting our shorelines, it's intensifying storm impacts, and altering how fresh and salt water interact across coastal systems. Especially in a place like Long Island and the South Shore, we very much are where fresh water meets salt water. And so we try to break down that bifurcation in an indigenous epistemology. Water can manifest in so many different ways, and all of those ways is deserving of protection. But what I also want you to take away from these images that I'm going to show you next is that maps and projections are never neutral. Behind every flood line is a lived world. Behind every model is a community. Behind every risk zone is someone's home, somebody's burial ground, somebody's drinking water, and our futures. And beyond the human, there are marshes that you can see here. There are shellfish beds and fish habitat, bird pathways, eelgrass meadows, and the countless living relations that make our coastal life possible and have for millennia. But as indigenous communities, a little bit of a switch there. There we go. We've got a great tech team. Thanks. But as indigenous communities, we are too often not included in climate planning. So a lot of the work that we've had to do as nations in recent years is to try to overcome many of these systemic barriers that have been placed before us. So before we even get to impacts, what I want you to understand is, again, these maps, these projections, these models, they're not neutral. And what we're seeing is a systemic playbook that before we even get to the impacts that are facing us in real time is built on a process and knowledge system of injustice, and that has promoted injustice over the years. So this is our territory in current and recent years. And under the sea level rise projections, this is our territory in give or take the next 50 to 100 years. You can see that that's almost under the high projections, 50% to 2/3 of land loss in the next century. So when this projection is overlaid onto our homelands, what appears is not only that water is moving inland, what appears is a confrontation with a planning system that was never built around indigenous permanence. We were not expected to exist alongside the United States. The United States was fundamentally designed for our extermination, and yet we still remain. So what do we do? What does that look like in contemporary climate governance? Well, for communities like mine, these maps are not just showing environmental change. They are showing shrinking land bases, fragmented jurisdiction, chronic underinvestment, and policies that still too often treat tribal nations as one stakeholder among many, rather than as sovereigns. So I want to emphasize this point here is that we are not stakeholders, we are nations. Not recognizing that furthers these constraints, and they not only affect our communities, but also the ability of animal kin and coastal ecosystems to remain in balance. When shorelines are hardened, when wetlands disappear, when water becomes contaminated, the harm moves across the whole web of life. Fundamentally, what I'm showing here is in the next 100 years, we are killing Mother Earth. So we've heard a lot about numbers, and the numbers are stark. 6.9 feet of sea level rise by 2100, under some projections. What I also want to emphasize with this slide, though, is a sense of resiliency. I mentioned that my community, communities throughout this region, we have been here for thousands of years. So we have seen sea level rise. We've seen it throughout our history. What is different is the rapidity of change that we're seeing in recent years and decades, as was shown earlier by colleagues. But despite that frequency of change, we do have vast amounts of knowledge of how to adapt, ways in which to think about strategies and solutions. What we also have to recall, though, in the context of these projections, is when we are modeling, what questions are we asking? Are we asking who is most exposed? Who has been excluded from planning? whose futures are being treated as negotiable, or as Dr. Bullard would say, whose flood zone becomes a sacrifice zone for the capital scene. We are not in a climate crisis, we are in a human crisis, a crisis driven by greed and exacerbated due to crises of governance and injustice. So the question I want us all to sit with today is, what does sea level rise actually mean for tribal nations? You might even ask yourself, what does sea level rise mean for me? It's probably one of the questions that brought you here today. But there is a bit of a distinction between what it may mean for you if you're not Indigenous, don't know, but I assume, versus what it means for myself as an Indigenous citizen and the tribal nations that call this region home. So I want us to think about this question not in the abstract, but on the ground, on these shorelines that we're now standing upon, thinking about it in the context of homes, of governance offices, in food systems, in ceremonies, in burial grounds, in the everyday labor of what it means to stay in relation to place. For Indigenous nations, sea level rise is never only about inundation. It's about whether we can continue to live lawfully, responsibly, and culturally in relationship with homeland. It is also about whether our more than human kin can continue to thrive alongside us. This is a different measure of impact than most adaptation frameworks are designed to see. So, looking even more specifically in the context of the East, because there are thousands of tribal nations across the continent of North America. There are more than 575 tribal nations that are federally recognized in a government-to-government relationship with the United States. And each of them has a relative uniqueness of how they are dealing with climate change and extreme climate events. And so particularly here in the Northeast and Mid-Atlantic, we have some regional uniqueness that has situated the acute problems that we see in relationship to sea level rise. So Eastern coastal tribal nations were regionally distinct. We have long histories of coastal stewardship. Many of our territories lie in low elevation coastal zones. And what's really important to understand here is that our current territories may be situated in those low-lying coastal elevation zones, but that may not have been the vastness of our historical territory. And we often had summer villages and winter villages, and we moved with the seasons and with the tides. But then due to colonization and illegal land takings and the evolution of urban sprawl and population growth and a whole big thing of federal Indian law that goes beyond today's lecture, we're confined to our existing territory. We can't legally move. And so it's a process that I often call being forced to drown in place. So because of this, our adaptation is shaped not only by climate change, but by ongoing settler colonialism. Climate change, therefore, does not arrive on a blank slate for us. It arrives in places already structured by dispossession. So many Eastern tribal nations, we've remained in place. We are on our ancestral territory, even if it's been diminished. But under these conditions of reduced land bases, constrained authority, contested recognition, it has exacerbated the experience of this contemporary climate crisis. So when people ask why tribal nations face such acute sea level rise challenges, the answer is not simply geography. It is geography plus colonialism. And it is also the fact that colonial systems have so often ruptured the relationships that allow both human and more than human communities to flourish together. So now that we've named the big elephant in the room, it's called colonialism and it still exists, let's move on. So what are some of these distinct impacts that we're seeing? So things such as increased flooding, permanent inundation of tribal coastal areas, wetland loss and migration, saltwater intrusion, drinking water contamination, cultural resources loss, as well as displacement. Now, each of these could be its own lecture for today. So we don't have time for that, so I want to focus in on one area specifically around drinking water contamination. And so when we look at drinking water contamination from a tribal perspective, tribal nations, we face distinct challenges when it comes to water security because of increasing SLR threats, sea level rise threats. So when we're thinking about that, what we mean is when I'm highlighting drinking water contamination, it's because it's really one of these core epistemological but also practical areas of our life as indigenous peoples on the eastern seaboard. So many of our nations, we rely on wells and septic systems as well as groundwater aquifers throughout this entire portion of the eastern seaboard to supply both our fresh water as well as to manage our wastewater systems. Now, these particular infrastructural setups, they are particularly prone to impacts from sea level rise, so things like saltwater intrusion, as well as flooding. And it just creates a whole lot of mess that has to be taken care of. But it's more than simply a utility issue or the provision of clean drinking water or the insurance of clean sanitation. It is not only a public health issue, but it's also coming back to that issue of sovereignty. If a nation cannot reliably protect and govern its water under worsening climate conditions because of chronic underinvestment and political constraint, then the failure is not simply environmental, it is structural. And when water is contaminated, that harm radiates outward. It affects our communities, yes, but it also affects fish, birds, marshes, and the ecologies that depend on clean and balanced waters. So in this essence, as we think about that earlier concept of sea level rise being directly connected to water justice, it's because water justice must be wide enough to hold space not only for humans, but for the non-human world as well. So these challenges related to water security are compounding experiences for indigenous nations. So we have issues around infrastructure, population growth, flooding and storm surge, land loss, as well as wastewater challenges. And the pressures often converge. So when we think about infrastructure, we may not have sufficient infrastructure, or like many parts of the world, we may have aging infrastructure that can be particularly susceptible to an extreme climate event, including sea level rise. We can have flooding and storm surge, where if you are reliant on septic systems, groundwater wells, et cetera, those can be directly impacted and perhaps unusable. We talked about Superstorm Sandy earlier today, and that was really the awakening moment for many throughout the region, indigenous and non-indigenous, of how dire these events can be if we haven't planned appropriately. We also have this compounding issue of land loss. So where are you going to put additional septic systems? Especially, I like to focus on poop and septic because I feel like it's a really good example. On Long Island, we have very, very old septic systems across the island. And many of them are working through processes with local townships and counties to be replaced, and sometimes there's grants and things available. Those are not available to indigenous populations. So many of the planning supports that were talked about today, some of the equity beneficiaries that were talked about today, indigenous nations don't get access to that, even though we do pay state and federal taxes. But if you look at the fine print of where those adaptation grants are available to and who they're available to, it doesn't include indigenous reservations or territories. So there's been this, again, grave injustice that's happening. And so coming back to septics and why that's important is if you want to get away from a cesspool system into kind of a nitrogen-reducing septic system, those can cost upwards of $50,000 to install, where the average income on the reservation is about $23,000 a year. You're not putting in a septic system. So there have been initiatives through the Indian Health Service and recent court cases that are coming down that do say that the federal government has an obligation to ensure clean sanitation and water for all. And so we'll see if that begins to shift some of this in coming years, but it still doesn't address the legacy impact that we're facing. So these are some of the ways in which there is distinct impacts to Native people versus other populations in the region. But despite this, indigenous nations continue to respond, we continue to govern, we continue to think about ways to innovate when we are dealing with these immense challenges. So, when you understand that you have sea level rise impacting a township, a tribal nation, a nation like the United States, what do you do? Well, that was the question that we asked. And usually you go to sea level rise adaptation frameworks, or SLR. And so I said, okay, let's take a look at what's out there. We're seeing tribal nations throughout the Northeast and Mid-Atlantic be directly impacted by sea level rise. How can we address this? Well, as was shared earlier, what we often see are, this was actually from I think the 2019 IPCC report on sea level rise. It was the one when I was crafting this research that you'll see the article in just a moment, was where everyone was going to. This was the cutting edge science of all of the global scientists coming together to say, here's how we address sea level rise. And this is what they gave us. Sarcasm intended, perhaps. So it was planned retreat, accommodate, protect, attack. We've heard this earlier from some of my co-panelists, which is great. The acronym is also called PARA. But I looked at this and I was like, there is no way any tribal council is going to look at this diagram and be like, yeah, that's going to work for us. So in the work that I do in trying to assist with climate adaptation science, which is also a behavioral science of how do you induce behavior change, I had to think about, okay, what's going wrong here? Something felt off, but I didn't have the words, the precise words, to name what was wrong. And so I, as all scientists do, look to the literature. And what we actually see is that there's been a history of adaptation colonialism. So colonialism, that elephant in the room, it permeates all facets of our lives in the ways in which we exist today. And it is definitely impacting sea level rise. So Marino wrote a wonderful article in 2018 suggesting that this concept of adaptation oppression, to highlight that Western scientific and cultural biases are reflected in the limited adaptation options present in existing frameworks. So basically, people are being confined to a cookie cutter, one size fits all, and that's not a good approach to science, innovation, and adaptation. And then Hardy et al., also similarly around that time, they said that existing processes for developing response strategies to climate change promote something called colorblind adaptation planning that overlook racial inequality and systemic racism in environmental governance institutions. So basically what they were saying is, it's not a blank slate for everybody. There are already existing pressures and systemic injustices that exist in our society that make the experience of sea level rise and thereby what you need to do for adaptation different for different communities. And so how we adapt needs to be context specific and localized. But even more than that, building off of what Hardy et al. And Marino had written, I took another look at this from an indigenous epistemological perspective, and I said, what are going to be some of the challenges to a tribal council, to an indigenous government adopting these types of measures? Well, first off, the language is very militarized and combative language. Now, we heard today who have been the folks that, for better or worse, have been charged with leading these initiatives. The Army Corps of Engineers, Army. They're housed in the Department of War. So you're inherently going to have militarized language. There's also a whole slew of literature and abolition ecology and so much more that you could do a deep dive on that, and the way in which how we have harmed militarily other parts of the world is now being used to save our ecology. There's problems with that, systemic injustice problems with that. And indigenous peoples, they see right through that, and there's no buy-in, so they're not going to embrace language of that sort. There's also no cultural connections here, so the colors are, I don't know, bland. It feels like bland bread, bland soup that you might get. There's no color, there's no design, there's just a square box that is a very westernized style of house. And it's also very human-centric. You don't, it's human-centric because you know that the house is something that a human lives in, But outside of the water, perhaps, and even the water is sort of vilified in this image, you don't see animals, you don't see plants, you don't even see a human. So if people can't see themselves in the adaptation measures that are being prescribed to them, how are they going to be convinced to actually adopt them? And so ultimately what we came out with is that adaptation is not neutral. We have historically relied on colorblind adaptation that reinforces inequality and excludes indigenous nations. But despite all of this, indigenous peoples are resilient. We are regenerative. And we have to acknowledge that. We have to lean into those principles and those ideologies, because if we embrace deficit language, indigenous or non-indigenous, if we embrace deficit language, if we embrace language of disappearance, of loss, of harm, we're really feeding in to furthering perpetuations of climate anxiety, climate doom, climate apocalypse, and you become the condition you set for yourself. So as indigenous peoples, we want to imagine something brighter, something bolder. And that's where the wampum framework came from. So this is an open access paper that's available for anyone that wants to scan the QR code. So what is the wampum framework? Well, it stands for witness, acknowledge, mend, protect, unite, and move. You can see here, again, it's building off of those treaty relationships, it's building off of that living law, it's building off of this idea that an understanding wampum is a part of our cultural identity in which we put good medicine, good words, truth into the world, healing into the world, that we can embrace adaptation that is not extractive or hardening, but that is caring, and that is healing, and that is loving. And so the principles, witness, acknowledge, mend, protect, unite, and move, I'll go through as we transition into our next portion of today. So witness is witness warnings from human and non-human relations and follow the patterns of the natural world. So first and foremost, throughout the Eastern Seaboard, as indigenous peoples, we have been witnessing our non-human kin experience a lot of harm, but also changing their patterns, shifting things. And so first and foremost, as indigenous peoples, we look to those we call them our elder brothers, our elder sisters. Those species have been here longer than us. We are the youngest species on this planet. And so being able to look to them to understand how they are adapting is our first process step in how we think about adaptation as Native people. Also, we then move to acknowledge, and this is acknowledge traditional teachings and restore cultural stewardship practices. Again, I won't have time to go into each of the different examples of how these adaptation strategies are deployed, but the paper does go into them if you want to dive a bit deeper. But why I focus on acknowledge is, in this moment, is in large part because, again, understanding that colonialism made it illegal in the United States as an American Indian to practice our religion until the late 1970s. So we did not have religious freedom in this country. We weren't even considered citizens until 1924. And under the current administration, they're even trying to remove that, if you heard recent transcripts from the Supreme Court. So this ability to practice cultural and traditional and religious process is under threat, and it has been. And so when we are able to do that, when we are able to continue these processes, it's very healing, not only for us, but for the land and for the water. MEND is the one I want to focus in on today. In this context, it stands for Mend the Shoreline and Practice Healing for Coastal and Environmental Sovereignty. And so what this looks like, I didn't say it at the top of my talk, but Shinnecock in our language, it means people of the stony shore. So after Superstorm Sandy came in and decimated much of the eastern seaboard, including Long Island and the Shinnecock Nation, we saw that there was a loss of stones, of boulders, of all of these different types of wave diminishment, nature-based solutions for our territory. And so we said, well, as people of the stony shore, our ancestors knew and embedded that knowledge in us that we have to maintain that shore. we have to maintain those stones. And so that is what really lent itself to our prioritization of stone and boulder replenishment and how we thought about maintaining our beach and building it back after the storm. We're not alone in these ideas of living shorelines. The Pamunkey Indian tribe as well has done this. They also exist on a peninsula. Interestingly, to Dr. Serafino's talk yesterday, they are a community that is inland, but is directly impacted. You can see here sort of the Chesapeake Bay region. When you have those riverine and ocean systems coming together, sea level rise can also impact the inland communities. And so they've been doing some really cool projects with how to adapt and create living shorelines. The other item is protect future generations by protecting cultural sites and ancestors. In the article, we talk about the ways in which we are looking at underwater archaeology and submerged sites. So I mentioned that we've been here for thousands of years. So in that context, I'm not just making something up. I think some people, might consider that, but the archaeological record shows that. So we've been here since the outer continental shelf was exposed. And so we had fishing villages, we have Clovis points that have been discovered. So it dates our continuity to this region very far back, and also contributes to that understanding that we have seen the sea change, and we have always been able to adapt to that. But what was different was our sovereignty was intact, and there was an understanding of peaceful coexistence. There was an understanding that our futurity is connected to one another. And so if we are healthy, then you are healthy, and vice versa. So this principle is really, how do we restore that? How do we make sure that we're protecting, not for ourselves, but for future generations? Unite is unite with other communities to build capacity and plan relocation. This is in large part because indigenous nations in the Northeast and Mid-Atlantic, we are smaller nations due to colonization and just other ways in which our political governance has evolved over the years. And so there's strength in numbers, there's strength in learning from one another. And I think in our current world and geopolitical climate, this is true not only for us, but for everyone. We can learn a lot when we work together rather than trying to fight one another. And so the last principle as we transition is move. And this is move to new places with cultural connections and rebuild. And what I want to emphasize here is that this principle was put in place largely for an aspirational statement. Because as I mentioned at the top of my talk, we are legally not able to move. There's no way that we're allowed to move. And so there are legal fixes to that, there are legislative fixes to that, none of which have been adopted or moved forward. And so we currently are constrained and confined to drown in place when it comes to sea level rise. There are many indigenous leaders that are trying to address this issue, but I think it's important to understand that it's an aspirational statement in large part because historically we would have moved, we would have adapted to the seasons. And very much like the Netherlands were mentioned earlier, the Dutch and many on this continent are trying to learn this. We were very conscious of how to live with water, not fight against it. But our current legal system, how we plan, how we consume, how we prioritize property in this world, does not allow for that movement anymore. And so perhaps we can re-envision a future or vision a future where that comes back and where maybe you are able to learn, everyone, indigenous and non-indigenous, how to live with water. So I heard my colleagues earlier, we need to end with some hope. And so when I fail to find hope in my work, which unfortunately is quite often, I go to everyday people who are living their lives working to protect this planet. And so I'm going to share some of those stories with you through a film that we did in just a moment. But I want to close this portion of my talk with acknowledging that tribal nations are sovereign. We are in government-to-government relationships with the United States, with Canada. We are akin to other nations around this world. And so climate adaptation is a governance issue. It's also a responsibility of everyone in this room and beyond to protect the water, and to protect the shore. And thereby, adaptation has to support self-determination. It has to recognize the inherent rights of nature. It has to recognize the inherent rights of indigenous people to be able to thrive and flourish together on this planet. So although we are seeing increased risk to coastal communities that presents vast implications for regional security, global sea level rise adaptation frameworks, they fail often to include indigenous peoples and knowledge in the development of these adaptation strategies. And so we refuse them, and we build our own. And it's not just us. Others need to do that. We need more localized and context-specific adaptation strategies that really lean into the beauty and power and regenerative capacity of everyday individuals and society. And so with that, I want to take you to the Women of Wampum. This is a film based on a gathering that we held with Indigenous women last May on the ancestral shores of Cape Cod and Martha's Vineyard. And it focuses in on wampum, on quahogs, and understanding how in protecting this species, we are protecting all life on this planet. So with that, I'm going to turn it to our wonderful tech team to press play. Or do I? There we go. So I don't have much more to say. I leave you with the voices of the women of wampum, but I appreciate all of you in having us here and being able to share their voices. I think as we close out today and we think about what comes next when we're dealing with these big, complex, wicked problems, I think we go back to the makers. We go back to the women who care for our homes, for our hearts, for our families. We understand that planning and adaptation is not gendered. It can and should have women's voices at the helm, and it really is going to rely on us as a human society, valuing the creatives in our world, the people who are able to see beauty when we feel like none exists. So with that, Tabutni, thank you for having me, and I'm happy to go to questions or our panel, but I'll leave it to the staff to decide. Thank you. The ball is making its way to you.
Yeah, of course, yes. Hi. So this is kind of about the actual process of granting personhood to a body of water. So one, how would the status of personhood like be implemented, and would this be through courts, like through like maybe case law and like precedent, or would it be an actual piece of legislation?
It's an excellent question. So the question is, how do we recognize the inherent rights of nature in our contemporary legal systems? So the lawyerly answer is it depends, but what I will say is that colleagues and I, we created an international database that tracks all of these different legal initiatives. It's called the Eco-Jurisprudence Monitor. If you go to ecojurisprudence.org or you type in Eco-Jurisprudence Monitor into Google, it will take you there, and it's an international interactive database, mapping database, where you can look at initiatives that may have been passed or tried to be passed in your local jurisdiction, your country, and other parts of the world. In the United States, there are a few different ways that rights of nature, earth law mechanisms can come into place. That can be through legislative measures like a town or city council resolution, can be through ordinance, it can be through codes and codification. It can also go through litigation or judicial precedent setting, as you mentioned. It also could be through administrative law or some other type of governmental decree, declaration. So there's a lot of different ways that these laws come into existence, and they all are different. They have different ways of recognizing rights. For indigenous nations, largely in the United States, it is through the indigenous government that usually starts by passing what is called a TCR, a tribal council resolution, and then that goes into a process of codification to become legislation through codes and ordinances. Thank you.
Lizzie, and mine's a bit more of a personal question. So I'm from Arizona, and I live by the Navajo and the Hopi tribes, and they kind of have more. They also have like a issue with water, but it's more of a scarcity issue rather than a sea level rise. Which I know this is a sea level rise symposium, but I just wanted to bring up that I really like this adaptation framework, the witness, acknowledgement, protect, unite, move. And so my question is kind of a two-parter. The first part is like, would you recommend, like, I know this is like your approach is more eastern coastal, but would you recommend a different adaptation framework for the different, I guess, areas of the United States of America and the different tribes that face different issues with water in the regions? And then also, like, the second part to that is, how do we approach ensuring that each region of the United States has some form of framework and like kind of on the more international scale of that?
Excellent questions. So the first one, if I can maybe paraphrase, is do I think the wampum framework can be applied in other contexts? And I think in large part the answer to that is no. I think it can be an inspiration for other contexts, but we really need to have, I did not envision this, although it did kind of get picked up in that way, and I'll talk about that in answer to your second question. I didn't envision the wampum framework being so well received by the national and international planning community, but then also everyone wanting to like take it and like, I want to use it here and I want to use it here. And that is great in the sense of it's starting a conversation, but it's not the end point. These adaptation frameworks need to be localized, context specific. They need to be driven by community voices, and the community needs to be present and represented, and culture and beauty and design, and that isn't something that you can just copy paste in terms of the wampum framework. So I hope it's a starting point, but not the end point. And in the context of Navajo and Hopi, I'll just say, I think tribal nations are already doing this. So it also answers your second question, which is, how do we get there to be more of these localized, context-specific adaptation frameworks? How do we get people to be even aware of the wampum framework and these other examples to sort of be valued in the broader international planning and emergency response community, et cetera? And so there's twofold there. When the IPCC and the US National Climate Assessment failed to adequately consult and engage and have authorship of indigenous peoples, then indigenous peoples made our own climate assessment, and it's called the STAC report, the Status of Tribes and Climate Change. It's going into its third volume. I was an author on several chapters for the second volume that was just released this year in January. Or maybe it was fall, might have been fall. But it's a great resource, and in there, and in the STAC report number 1, which was done a few years ago, we also talk about the Great Lakes Indian Tribe and Fish and Great Lakes Indian Fish Wildlife Commission, there we go. And they have a wonderful climate change adaptation menu that they made back in 2016, where they also took a very localized Anishinaabe approach and perspective for working with climate change issues in the Great Lakes. So I think tribes around the country are already doing this work, and so you can see that there in the STAC reports. And then what we also are seeing is, as we are able to tell our own stories, have the wampum framework out there. Again, as I mentioned, it's been very well received by the global scientific community. And so in the recent NCA 5, which the administration has scrubbed from, all websites, but it's in the archives, you can go find it. There is Indigenous Peoples chapter, it's mentioned there, it's mentioned in the Northeast regional chapters, and we also now have a good stronghold of Indigenous scientists who are being represented in the current drafting of the next installment of the IPCC report. So I think we are making progress, but again, there's a difference from Indigenous peoples and scientists being integrated into an already established colonial system of climate assessments versus us doing our own. And so I think there's space to do it all, and if I, don't like sleep, that's pretty much what I've done. So you can also find this work and my work in the New York State Climate Assessment. Thank you. It's coming. Yeah. The lights are a little blinding down here.
Okay, just real quick, can you go back to the QR code you had up on the screen?
Sorry if anybody gets dizzy. There you go. Okay. Was that your question?
That's all, thank you.
I love
just
it.
wanted to
Thank
read
you.
more.
It's a good way to end. Thank you all. Take care.
So thanks to Dr. Leonard and all of our speakers today. We've been here, I think a break is a good idea, so I'm going to propose maybe 15 minutes if we could come back about 5 past. That'll give everyone a chance to stretch your legs and get some refreshments upstairs. I hope you'll stick around. I really would love for us to reconvene right here, say 5 past, for just more casual discussion with all 5 speakers on a panel, and that'll give us a way to wrap up the day in a nice way. So, and I also one more request for Goodwin-Niering students. If you could hang out afterwards a little bit too, we might need a hand with a few things at the end. So thanks. We'll be back in 15. Thanks, everyone. Yeah. can we say thank you to Sabila? Would you like to take a bow? Sabila, you have made Sabila Alibhai, our pianist. I mean, oh my God. We're really grateful for your joining us and bringing the music today. It's just absolutely wonderful. So thanks. Can I thank all 5 of our speakers before we go any further? Just thanks to all of you for wonderful talks. I just couldn't be more excited at kind of what's emerged from all, the combination of your talks this weekend. So this is a little bit casual. We're a little bit behind schedule, but we were just thinking maybe we could see how it goes with conversation. I'm thinking about 4:45 as a possible stop time, if that makes sense. Or we could just kind of be flexible and see how it goes. I have a couple questions for the panel myself, but I thought maybe we could open things up a little bit to start with, and maybe if anybody has any like pent-up questions from earlier in the day for a particular speaker, or maybe a question you'd like to hear everyone weigh in on. I can't see too well. Oh, there is a hand, yeah. Mm-hmm.
Thank you. Thank you all so much, and thank you to the Goodwin-Niering.
Perfect. That's a nice way to start. Thank you so much. Yeah, Lisa.
Oh, I was just going to say, I really appreciated your alternative framework for thinking about that, and it reminded me of some overlap work that's happening in the philosophy of data with the CARE data principles. So oftentimes people talk about the FAIR data principles, but they don't actually mean FAIR. It's a very misleading acronym. It means findable, interoperable, accessible, which is just sharing of data. But the indigenous scholars have developed this wonderful CARE framework for thinking about data too, and it reminded me of that work and that overlap, and the importance of really kind of challenging some of these sort of standard ways of approaching this and thinking much more in terms of kinship and care and responsibility when it comes to things like scientific practice and scientific data and so forth. And so I just appreciate that. I was wondering if you had worked at all with that framework as well in your work.
So thank you for the comment and the question. I'm chuckling a little bit because it might have seemed similar because I'm a co-author of the CARE principles. But yes, for those that don't know, I think you did a good summation of it, but the CARE principles are indigenous data sovereignty, particularly indigenous data governance principles for how we think about managing data in our very globalized world. And so, and when I talk about them with scientists, like all of us up here today, is, how do we shift from thinking about, Vine Jr. is a really wonderful Native American scholar, since passed away, but left a legacy of scholarship and philosophy. And he always said that there is this myth of scientific objectivity, and that we need to break that down, and we need to lead science with care and with love and with an ethic of care. And so I see the CARE principles and this work that we've been doing on indigenous data sovereignty as a response to this idea of scientific objectivity. And in reality, science is not objective. We all bring our biases, good or bad, into the science that we do. And if we can acknowledge that, then it's the first step in being care-filled human beings with an ethic of care for other humans on the planet.
Maybe I could just follow up.
Oh,
if you
absolutely.
Want,
Yeah. Oh, sure. Go ahead.
To fill in some things. Also, again, I apologize. I always start with a comment, but I really appreciated also the colonial aspect, and I just wanted to highlight some of the overlap. I mean, I'm just thinking of connections between our talks, so that's kind of the approach I'm taking to this panel at the moment. But thinking about what you were just saying, especially the issue of bias in the data, and I think that's a really big issue in the geosciences where so much data is being collected in the global north, and it's also, questions ranging from gaps in data in the global south, biasing our understanding of the Earth system. And this came up, I guess, with Chris's talk, thinking about how satellites in some ways are compensating for that, but you still need sometimes on the ground or on the water data to work with, as well as the satellite data. But also thinking about how issues of data collection on indigenous land and the sharing of that data in a way that harms the broader, as you say, kinship of that land, and so forth. So there's just so many issues that have to do with the kind of issues of colonialism, both the biases and the harms that can come from that, and how it's important for all scientists who want to make progress on these questions to address these issues. So I appreciate it. Thank you.
Yeah, I mean, to what Chris shared and what you just brought up, I think we really do have a challenge in the governance world of the United States and Canada and globally. We like to say this term, best available science, that we're using the best available data, but we actually have a data deficit. We're not collecting enough hydrological data, both in sort of in terrestrial spaces in the interior, but also along the coast. So the more that we can have substantive data to be able to make informed decisions, the better. And then, to the CARE principles, it's not just collecting the data, but it's how do we steward that data and make sure that community has access to the data to be able to make informed decisions about how to respond to the changes that they're experiencing. And so, I think the work that you're doing is really excellent, because the more that we can democratize data collection and the sensory way in which we're able to deploy that technology, the better we all will be for it.
Can I throw something in there? Sorry, Katie, I'm going to put you on blast. So related to these ideas of stewardship, Katie, you were asked a really interesting question last evening about AI. And I'm wondering how, again, perhaps leading off from this previous answer, what all the panelists take on the proliferation of AI in whatever sort of embodiment you want to choose, and how that bears on the topics we talked about today. I guess I'll start. I mean, I found it really interesting the way that Katie responded. For better or worse, I'll summarize my take on AI with, I seem to have cultivated a reputation that people feel the need to apologize about their use of AI around me. I was telling someone yesterday, it's very interesting when you get into the sciences, you find yourself in a community where, you're on the same page with most people most of the time. You're both passionate about the same things, and more than anything that I've experienced in my career is the topic of AI. I've just, in a way that I didn't anticipate, you get such disparate, wide-ranging responses. A lot of colleagues I have, very similar to Katie's response, is embracing the technology and seeing all the ways that it can benefit our science. I tend to, I won't say be skeptical of it. I do think it raises a lot of fundamental questions that fall into the realm of philosophy of science and what science is and knowability, especially the black box culture around the use of AI. But anyway, I'm less interested in my opinion. Again, I've told you where I stand, and that I have a bit of a reputation around my department for my, yes, the opinion I have. But I'm curious what the other panelists would say. Or maybe I can let Katie respond.
Well, I'll just make a quick follow-up statement. I did say too, I think it's really important. I think there are tools that can be used in ways that can help with some of the questions that we're asking, for sure. But I also think they come with caveats, right? Like in our understanding, I know that Chris comes from a very fundamental physics-based world, and there's still a lot of things we don't understand in the different connections across some of the algorithms that are being used in AI, right? So there's a whole lot of people trying to understand, like how we can add physics-based formulations into our AI models. But then you can think, I can't talk as much on this, maybe other panelists can, but on some of the ethics in the type of data sets that these models are learning from, right? So what biases do they have? And then also the sustainability perspective, right? We're putting out lots of computers that take a lot of energy. Some places they take up a lot of water resources. And so thinking very, we are always very into all of the benefits of something new and cool and exciting, but it's just like, right, everything might have an unintended consequence that we don't think about quite as deeply when we're so excited about the usefulness of something new.
Just say one quick thing to hand it off to the other end of the room, and because Tammy was reaching for the mic, I hope that she'll also say something about AI and capital. But the word I was looking for is Luddite. That is how I am known.
Katie's response last night about how scientists were using AI inspired a conversation at our dinner table last night when we were actually saying, oh, well, maybe there are some good uses for AI. And as a sociologist who studies environmental justice issues, I absolutely agree with what Katie was just saying around the sustainability issues. So we have to think about where are data centers for AI being located? Who's making those decisions? Do local people have input into that decision making? The water and the energy use. What happens when our energy use is going there first and not to, say, residential users? So that would be the first take I have. And secondly, I think this is a bigger question about democracy and science and who's making decisions about what kind of innovations we're working on, what kind of science we want. We don't see a lot of impact science. We see a lot of science that's directed toward R&D for things like AI. And so the people who are making the decisions about science are the people who have the money. And it's not necessarily the democracy. I don't think any of us voted on, we should put funds toward AI. And so I think the question of who decides is really critical here, and who's deciding about what gets, where the funds get invested to do this research and development. And it's mostly, we're seeing a shift now too, where there's less and less public funds and more private funds. And so we don't really have a say, and I think that should concern all of us.
So I think you've highlighted many of the key issues, the environmental issues. There's also the sort of issues of the training data that a lot of these large language models were built on. They need vast quantities of data. The quality of the data is not always very good data, and it can have a lot of biases in it. And so there's been all sorts of examples of AI, for example, not hiring, recommending that women be hired for jobs when they do the auto checking of CVs, because traditionally more white men have been hired for CEO positions than women, and so the AI model learns white men are the best for CEO positions and then pushes that forward. And so there's been all sorts of examples like that. There's been examples of racism in medical AI, so many medical AI algorithms that a lot of doctors and nurses might be consulting these AI systems. They haven't been properly vetted for a history of scientific racism about medical issues, about non-whites, and assumptions that were made back in the time of justification of slavery. And yet they're still spitting out these answers that blacks don't feel pain, or that women, whatever. So there's real issues that I think we've rushed too quickly forward to implement these AI systems in very high-stakes contexts without really understanding how they're making the decisions they're making, what kind of data they're drawing on. They've been black boxed in a way that's very hard to interrogate. and it's also being set up in a way that it's hard to hold morally responsible, right? The first assumption is, oh, well, it's a machine, it can't be biased, and so we're actually making science or decision-making, whether it be in recidivism of in a prison system or decisions about who gets hired or funding, but in fact, they're not actually more objective, right? Because they're built on a history of data that's already biased in various sorts of ways. And so I think there needs to be a bit of slowing down in the deployment of this technology in various contexts. I think it is a tool, and tools are useful in some contexts and harmful in others. You don't want to use a hammer to do a surgery. So you need, right now people are pushing AI as if it's the answer to everything, and they're rushing to implement it in all sorts of contexts without, I think, really giving sociologists and historians thinking about the data, thinking about the ethical responsibility of these issues. They're just offloading it on these assumptions that it's objective. So I think there needs to be a bit of caution going forward, and we kind of saw this where there was this jump forward to implement the technology without the adequate research on its broader social, ethical, and so forth implications. And so it's nice to see that there's now a move for that. So for any of the students in the audience, at Northeastern University in Boston, there's a wonderful summer school for students on ethics of AI in data. It's an extended program, but several top faculty. So we're starting, at least, I know philosophy is sort of was behind on this issue, but now we're starting to be able to train students in the philosophy of AI and getting curriculum opportunities such as the summer school, where we can start to sort of develop the literature we need to understand the implication of this technology and where it's okay to keep it going forward and where we should be pulling it back and proceeding with more caution.
Well, everyone said everything I was going to say, so I just concur. I think what I will perhaps add is that as members of society today, we have to be conscious about what we are complicit in. We all are making choices every day, and those choices have consequences, and we have to be held accountable for those consequences. We can't throw our hands up and go, I didn't know, when you do have sort of a wealth of information at your fingertips with the way that technology works today to be informed and to be understanding of the choices that you make. And so when we're thinking about sea level rise and AI, I'll go back to what others said in terms of energy consumption. We have a current administration that is not leaning into renewables, that is leaning into fossil fuels. So when we're building these big data centers, which much of them are relying on modular systems and generator systems on fossil fuels, they are increasing carbon emissions on our planet globally around the world, not just in the United States, but anywhere else that is building these data centers globally. And they're often disadvantaging, as others mentioned, certain communities. So there are certain people around our world that are being sacrificed so that we can access and use AI. And then to do so in the name of environmental conservation, we have to ask ourselves, are we conscious of who we're sacrificing for that choice?
Maybe just to add one other thing on the topic, I think people often think about these systems as information sources, reliable sources of information, but there's been a lot of research showing that these AI systems hallucinate, or some people call them bullshit machines, where bullshit is a technical philosophy term, actually. And so it's looking at a language, it's based fundamentally on a language prediction technology. So what's the most likely next word in a sentence, for example? And that's kind of the core. I mean, obviously far more sophisticated, but that's the core of the technology. And so it'll find patterns in, things that aren't necessarily the most reliable. So if you think about things where people make lots of comments about things, but they might not know what something is an expertise issue, then they're not going to be a good source. They're just going to go with what most often is said and not with what's the correct answer from the relevant experts. And so I think we also need to be rethinking this as an information source. It tries to connect to information sources, but it's often not returning reliable information from those information sources. And it's a step down. It's like a degraded lower resolution of information from the reliable source, because it is being compromised with all this information coming from non-reliable sources as well. And so I think we need to kind of weigh that as well as when we're using this technology.
Thanks so much. This is the best panel ever. Kind of as a moderator, I haven't do anything. Any questions? Oh, there's a couple. Yeah, there's a question.
Hello? What happened to the ball? I'm just kidding. Thank you, panelists. This has been such an interesting, 24 hours. So thanks all for sharing your expertise. My question is, can you tell us a little bit more about the boundary spanning organizations that you work with? And, who are the different types of people that you collaborate with regularly who are outside of your institution? And I'm thinking nonprofits, municipalities, who are the other people who are involved in the work? And then also thinking, especially as, we're at a university, okay, that's part one of the question. Then part two is what's the level of expertise of the people that you're working with? Do they have advanced degrees? Are they straight out of college? What can we think about when we're thinking about our, the center seniors and the next generation coming out into the workforce? Can they join the work that you're doing right now? And how? How do they get involved? Thank you.
Those are great questions. I'll try to be brief because I'm hoping to hear from everyone on the panel. So I'll use two examples. So one organization I work with a lot, who is represented here but a different office, is Sea Grant. We're fortunate at Woods Hole Oceanographic to have a Sea Grant office, which I can't remember whom, but one of the previous speakers today mentioned this idea of boundary organizations, and Sea Grant is a wonderful example of this. And so do quite a bit of collaboration with the Sea Grant office at Woods Hole. They have an office that works in coastal impacts. I wanted to focus on the word work with, because it's really hard sometimes to get funding to have the salary support to do research efforts or outreach. And so oftentimes that work begins before you're getting paid on the clock, and involves a lot of conversations and relationship building. So I wanted to highlight that one issue. And as for the level of training, a lot of them have advanced degrees. So the people I work with at Hui Sea Grant have advanced degrees in coastal management and marine affairs. There are folks I work with at the state level in Massachusetts who are doctorate level scientists in, I've gotten to this place where I remember the acronyms, but not the meanings of the acronyms. But we have climate scientists at the state level in Massachusetts who are doctorally trained scientists, which I think makes smoother that transfer of knowledge and interaction process. So that's just one example, or two examples rather.
Are we gonna go down the line? So I also have worked with Florida Sea Grant. They are housed at the University of Florida, so it's a fairly easy relationship, I guess, to get hold of extension agents and think about your reach across different coastal counties to help you figure out kind of what are the themes that the communities are interested in, and what are the important questions that they need help answering. But I've also, some of the work that I've done, especially the compound flood work on river systems, extends into the water management districts, which in Florida encompass kind of, I think there's 4 or 5 across the state of Florida, across major river systems, so thinking about the future flood risks in those areas. And then I had a unique relationship also, I think, with the Tampa Bay Planning Council, because they were leading vulnerability assessments funded by the state under a large amount of legislature that's funding billions of dollars in flood resilience research right now. Or not research, like grants and vulnerability assessments. And so They contracted a few researchers at the University of Florida to like have oversight of the or review the process. That they were like, you know, we have all of these state guidelines that we have to follow for submitting this vulnerability assessment. So can you make sure that our work is, you know, that we're aligning with all these guidelines? And then when they also hired an engineering firm to do some of the work, can you kind of QA/QC it to make sure that you think it makes sense and that they're doing a good job with it as well? And so it was kind of like an external advisory position for them to move their vulnerability assessments forward.
I talked earlier about the Science Resilience Institute at Jamaica Bay, so I'm not going to talk about them again, but I want to give students one specific example of a group that I work with. It's the Jamaica Bay Rockaway Parks Conservancy, and it's an organization that works with the SRIJB, our boundary organization, and they do stewardship work in Jamaica Bay, and they have a program for interns. I forget what they call them. It's something like the watershed interns, and so they have students come while they're still in college, and they also work with some high school students, and they participate with them in doing stewardship activities, but they also do research. And so they have some experimental, you know, living shorelines where the students come in and do work. And the reason I'm saying this to you is because a lot of their interns then go away, get their master's degree or their PhD, and they come back and then they're on staff. So take your internships seriously if it's the kind of work that you want to be doing, because it does have the potential to lead to something longer term.
You're good? Okay. Yes, so list of things. I guess first and foremost is I often work with tribes. So I run a lab at the University of Waterloo called the Wampum Lab. You can see it's all kind of connected. But within that, I often say to students or collaborators, we're an applied research lab. So we do questions, we look at questions that community brings forward to us, that community finds important. So they are co-researchers in all of our processes. So we're just kind of there as the vessels to do their bidding and their wishes. So that can be tribes. We also, you know, can work with other boundary spanning institutions or organizations like you mentioned. We also have a really great collaboration as a co-PI with the UMass Amherst Center for Braiding Indigenous Knowledge and Science, which is an NSF-funded science center called CBICS. So you can find them online for students. They have internships and things that are available. Sea Grant has been great. Anybody familiar with the regional ocean partnerships in the room? Because they do a lot in the context of sea level rise and much of what we talked about today. So those are like the Northeast Regional Ocean Council, NROC, MARCO, the Mid-Atlantic Regional Ocean Council. These are basically state regional partnerships that then bring in tribes, federal agencies, fishery management councils to work together for ocean planning and coastlines security. And so they're very foundational, and I've been a part of that work for, 15 or so years now. In New York, where we're located, NYSERDA has been a great ally and colleague. For the Earth Law Rights of Nature folks in the room, there's an organization called the Earth Law Center. I think they're really great for anyone, especially students. They take interns, undergrads, all the way through legacy fellows. If you're retired in the room and wanna do some work in your retirement, they take legacy fellows. And then across from that, undergrads, grad students, postdocs, staff, community-based researchers, farmers, hunters, artists, and then lastly, I had on my list botanical institutions when we're thinking about sea level rise. Botanical institutions, you largely think about terrestrial plants. They also house marine plants, which are integral to how we understand changes in seagrass globally. So we've been doing some cool work on changes in seagrass through botanical collections.
Questions from the audience?
Hi. I don't know exactly how to put my question into words, but I was kind of struck with this kind of depressing weight after all of this. And you're all amazing, and you're all doing incredible work. And I'm just wondering, you know, if when it feels like in politics right now in the U.S., someone can just like flip a button and change policies that have been there for a long, long time, or things that are helping the environment, it feels to me as an environmental studies major sometimes pointless to be trying so hard to care so much. And I know like everyone says you gotta have hope, and like I don't know if you have any other suggestions than hope. I mean, you're really like, you have committed your livelihoods to this. So like, as someone who wants to follow in those footsteps but feels very discouraged right now, if you think there's concrete things that I could be doing or that you have advice on. And if not, I understand.
We can't leave him hanging. So I'll tell you. Oh, I didn't touch anything. I'll tell you what it was like when, I guess it's about 10 years or so now, when I was finishing my PhD. And I was working with indigenous grandmothers on protection of water in the Great Lakes. And I said, okay, so there's all these horrible things happening, and you know, we need politicians to do things differently in the Great Lakes and to make different choices. Like, do you have any hope for politicians and for governance? And they just flatly was like, no. I was like, well, there goes my PhD. But then I was like, okay, well, if you don't have any hope for like the governance folks, like, who do you have hope for? Because I see that you are still here. You're living. You're thriving. Your nation. You're lifting up your nations. And they said, I have hope for the little ones. In Canada, a lot of the folks I was interviewing are in that sort of geopolitical context, and so those are JKs, so preschoolers. They said basically from baby to 5. They still are so close to that natal connection that they had with water, that they still see the world with such beauty and vision and hope, and being able to lean into those younger voices was where they said they saw hope, they saw change. And so for them, what that meant is governance doesn't have to only exist in the halls of Congress. It can exist in how we educate. It can exist in how we connect to the land. And so what they wound up doing was promoting educational programs in JK preschool curriculum, where students actually were moved out into the land to learn about water, to play with water, to have tactile sensory experiences that allowed for them to keep that connection to water. And so I lean into things like that. As I said at the end, the world could end tomorrow. And if that happens, wouldn't you, I mean, I know today we're in an auditorium and you're listening to us just espouse, philosophical thoughts, but wouldn't you love to have been able to say, yeah, I touched that water. I swam in that water. I know that tree lost a branch yesterday because I've watched and I've listened and I've connected. And I think, we just started with a conversation about AI. We're on a path towards disconnection in our society. And it doesn't mean that you don't have to take in those new technologies, all of those things, but how do you have balance? I hope that's a bit of what you can leave with today, is that you can't have hope if you don't have balance. You can't have hope if you don't know what it's like to have despotism. You have to have a bit of the horror in the world to know the beauty. But the key is that you're able to find that balance.
Yeah, and just to say that was a really fantastic response. I'm a little bit hesitant to go after that, but I just want to start by just acknowledging that heaviness, and I think it's important to acknowledge that. And I'm glad you asked the question you did. My take is words are tricky. I try not to talk about hope. I talk more about like inspiration and value, and I think this ties into what Kelsey was saying, because when you think about hope and power being these things that are locked away in the halls of Congress, then it's very disempowering, right? And it feels very, you get cynical. So this actually reminds me, I'm not sure if Sam is still in the audience, it reminds me, oh, there she is, a conversation we were having last night at dinner, which is kind of, what do you do? Like, why are you here? And I was describing, actually we were sort of connecting about this same pattern in both of our lives of, finding that thing that you're passionate about. Like for Sam, it's the outdoor recreation industry and making it more sustainable, right? And so finding the thing that you're really passionate about and then evaluating your sphere of influence, your privilege, your power, where you have the resources to make a difference. And all of a sudden, things become a whole lot more tangible and concrete and right in front of you. One of the things I talked about this morning is that I'm really excited to hold this, I've been jokingly calling it Sea Level Camp, the Sea Level Summer School in Woods Hole next month. And that to me was this perfect wedding of, I'm passionate about the science of sea level rise, and I think it's important that physical understanding enters in with other forms of knowledge to help us make decisions. And this was something that I could do in the face of exactly the things that you're talking about. Say, you know what? I can't control those things that are going on in Congress, but I can say, in the face of that, I'm going to use the resources that I have to try to solidify this brain trust of knowledge among young scientists. And will that matter? I don't know. It's a small thing, and it's something that I can do given my privilege and resources. So I think it's one of those things where, we talked about adaptation responses not being cookie cutter and needing to, be applied to a locality and its culture. And there's something similar about what do we do in the face of this, again, destruction that is very important to acknowledge the reality of it, to mourn that, but to find the particular ways that we are able to do something about that.
Two great answers. I'll follow up with one more. So I teach a class called Living with Rising Seas at the University of Florida, and it's a undergraduate general education class. So I get a diversity of majors. It's very interdisciplinary, much like the things that we're talking about today. And I ask a reflection at the end of the class that is, now with all this knowledge, do you feel hopeful or helpless? And, what's challenging reading those reflections is a lot of times it feels 50-50, that I left students feeling really helpless because maybe they weren't as educated on sea level rise as they thought they were, and now they feel very worried about the future. And so with some colleagues who teach a class on pandemics, we've been trying to analyze some of these reflections to look at, can we think about our teaching so we can teach in ways, these wicked problems, in ways that, don't make people feel more anxious or worse than they already do about it. So I think it is important to find inspiring messages and maybe hope. But something I'm very inspired about when I read these connections and their reflections at the beginning of class is all of these students have such connection to the topics that we're going to be talking about because they lived on the coast or they grew up on the coast. And they end with saying, oh, I can talk about this with my parents now. Or I didn't know that I could relate this to the work that I'm doing in some other field. And so for me, I'm inspired by the young ones, but the young ones being, college students like you all, and the fact that we're all here having this conversation as we go out into really different futures, profession and career-wise, even if we're focused on, thinking environmentally consciously about the world around us.
Yeah, I think as educators, we are hopeful, right? We believe that we can impart some education that will make things better. But I think the question that you ask is one I'm really concerned about, and one that I grapple with every day, and I think we ask ourselves, how do we carry on, right? And what's the use of carrying on? And what should I be doing? And what's really helped me is to see the long view, right? And to see that, no single person can do anything on their own, but it takes this long view. Rachel Carson, right? She's one of my sheroes, right? And I have a picture of her on my desk, and I just think, oh my gosh, what would the world be like if Rachel Carson didn't live, right? If she was never alive, if she never did her research, if she never wrote her book. But she alone did not, create the environmental movement and create, changes to legislation. It took a lot of people picking up on that same feeling and the research that she was doing. And so I try to think of myself as like, the work that I'm doing is not going to be the thing that makes the big difference, but what it's going to be is a continuation of work that's come before me, and then through my teaching, hopefully through my students. And so rather than seeing myself as an important person, I see myself as a thread, right? And that lowers my anxiety a lot. And then, going to what other people have said, doing the actions that I have the control over, right? I can teach my classes, I can have effects with my students, with the people who I interact with. And that's my job. That's why I'm here, and that's what I can do. So that helps me. The long view, seeing myself as part of a continuation and a team.
Feels like this might be a good moment for us to conclude our panel. We've kind of circled back in a way, to Stephanie Haskins' opening yesterday, and it feels absolutely wonderful that Rachel Carson comes up at the very end of our symposium on sea level. She was a marine biologist who wrote the book. Her other book was Sea Around Us, right? So it just feels like the edge of the sea, right? Yeah. So. Yeah. So, yep. Yeah, so it feels like this might be a really nice place for us to land. So I want to ask if we could thank our panel again. And thanks to all of you for spending your Saturday with us. We do have a reception set up above, and so everyone's welcome to hang out and enjoy the reception. I want to let the speakers know we are hoping to take a photo with Dick Goodwin and Bill Niering upstairs in the gallery with the cutouts, if you don't mind. Yeah. So thanks to you all, and everyone. Again, thanks for joining us, and enjoy the rest of your weekend.